Check, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ja, ich bin ein bisschen... So, läuft. Hervorragend, Pegel sieht okayisch aus, Limiter ist drin. Grande. Check, 1, 2, 3, 4, 5, 6, 7, 8, super. Dann läuft der Raum hier auch. Dann jetzt nur bitte beachten,
All right, and I'm unmuted. So, will we get a signal like when the stream starts and everything, or is it just continuing on going?
Are we good?
Are we all good up there? All right, we're good. So welcome everyone to JuliaCon. This is the year 2026, and one of the things that's really big about the year 2026 is agentic AI seems to be everywhere. In fact, there's a version of me that lives online, which has like a little robot costume around, and the talk that I'm going to give here today is exactly how does that whole thing work, what have been the consequences to open source maintenance, and how exactly have we changed the way that we do a lot of the work in the SciMO organization, right? So I'm Chris Rakakis. I'm the VP of Modeling and Simulation at Julia Hub. I'm also the co-PI of the Julia Lab at MIT. I maintain a lot of the Julia open source libraries. As you'll see, I think that the statistics say it's 209 packages in SciML plus a few hundred other ones, right? So I've been working on Julia for a very long time, and now a lot of this has agentic AI kind of morphed throughout it. And I think a lot of people have had a lot of questions of, is it working? Is it a bad idea? Is it a good idea? And the purpose of this talk is to really go through a lot of the pros and cons of what's been going on and how it's done. The main question is, can you vibe code without creating slop, right? I think that we're going to refine what we're calling vibe coding here, because you'll see it's not just, like, hey, make this web app for me. It's very, there's a lot more details that are going into it. I'm going to show you exact prompts, how they're working, how they're not working. But I do think that what we can say is some very concrete statements about what it has done in terms of correctness of programs, what it's done in terms of lifestyle, and a lot of other aspects, right? I'm going to park two debates right at the door, right? One, I'm not going to talk about the morality of AI. That is a very good conversation to have about whether, it's ethical, whether it's stolen a lot of copyright, I'm not going to talk about that here. I'm just going to say AI exists, and we're going to talk about the AIs that exist. I'm also not going to talk about prices. I'll make a statement about prices right now, which is that I have the two, $400 a month subscriptions. Well, both Claude and OpenAI, they give you these subscriptions for free if you're open source maintainer of enough libraries. And so for the two open source, for the two subscriptions, it's about $400 a month. I did the calculation. Over the last year, we've been averaging if it was priced for API, it would cost about $27,000 a month. This is all being paid for by the OpenAI and Anthropic's VCs right now. I think that there's a very good question about whether such a system is maintainable, whether it's going to happen, and that's a great market discussion. I'm going to cut all of that now and just say, yes, someone's paying for it. We're not footing the bill. But if someone else is footing the bill, is this a good way to do programming and to build open source ecosystems, right? Now, first point that I want to make here then is, has this changed the life of an open source maintainer? The answer is undeniably in the last year. This has completely changed everything about how I've been doing open source maintenance, right? Because the way that we had to do open source maintenance before is we had this throughput problem, right? The throughput problem is, okay, when you're trying to work on open source, you need to work on something, you make a commit, and then you have 20 minutes before your test finish, right? And so the question is, what can you do in that time? Well, the best thing to do is you get one commit, and then during that time you're waiting 20 seconds, you move over to 20 minutes, you move over to another tab, you work on your next commit, and you go over to your next tab, you work on your next commit. And you try to have about 8 pull requests that are continuously all working at the same time. And and as emails are coming in, then you might maybe answer one issue, you answer a discourse post today, and you're doing all this, right? But because you're continually trying to make your computers all work, that means that you have to stay at your computer the entire time. And every single moment you're away from your computer, it's no longer working. That is lost time, right? And so I think that a lot of people here, within the Julia community, know that it's no joke that I would probably spend about 16 to 20 hours at my computer every single day for the last 10 years, right? Like, this is documented evidence all around that this thing exists, right? And this is the reason why. Because if you were to ever leave, you have this throughput problem that you can never gain back the time that your computers were not running, right? But then, the thing that changes then is that now with the agentic AI, you can basically load it up where you can say, hey, look, here's all the problems that I want to run. Run this, run this, run this, run this, run this, run this, run this. And you can basically load up 40 to 80 different problems, and you just say, keep on running all these things. But as things are finishing, let me do let me check this on my email. Okay, now this is running, this is running. And literally, if you want to see the statistics for it, generative AI came out, and I was able to start changing my workflow. And I lost 35 kilograms in literally the first year of that coming out, right? And it's just, and I now DJ a karaoke show, and I'm doing more work than I ever had done before, right? Because the real key to efficiency is not how much can you force yourself to work. The real key to efficiency is, can I keep all of my systems continually running? And one of the things that you can do with the generative AI systems, you can say, hey, look, I'm going to be gone for the next 4 hours, but while I'm gone, please start working on this pull request, this one, this one, and then all the answers, all the code changes are in your phone. And as you're walking down the street, you can continually review code. And so the biggest change of using generative AI is actually that you can not be at your computer and still do just as much work. And I think that that's been one of the huge changes that we've been seeing in the ecosystem, right? And the quantitative effect here is that literally, in 2017, I made about 6,200 contributions. This is some of the most in the Julia ecosystem. We're going through 2026 right now with 17,000 contributions, and each of these commits, they've gone from a lot of commits that were like, fixed typo and like 2-line changes, to almost all of these are actually complete pull requests, right? And so there's been a huge improvement in the amount of code that's being done, because now instead of having to do every single change and then change, wait, now we're able to just kick off tons of changes and then continually just review what's going on. In fact, I could basically just open up my phone right here, and while giving this talk, I can review a piece of code and merge it while talking to you, everyone here. And you guys, if you could find out which repo I just merged something on, it'd be great, right? See, that's a complete change to the efficiency, right? Now, the key issue is how fast can you read code, make sure it's correct, and be able to pull things around, right? And now, you might say like, okay, but agents get things wrong, right? How much can an agent actually solve? My problems are too hard for an agent, right? I think the statement that I want to show quantitatively is that most pull requests that are going on in the open source community are easy, right? So, we have 217 public repositories in the SIMO organization. We have 302 packages registered to general, because some of these repos are actually multiple packages within them, right? If you actually do the statistics, what comes out to is that there's about 11 to 17 user issues or pull requests that have to be handled every single day, right? And what this meant before was, each of these things that one of you comes up with, I mean, people, you guys all have hard problems, right? You have a PhD and you're given discipline. So if you're going to come to me with an issue, it's not usually going to be an issue that's solved in 2 minutes, right? It's an issue I probably have to get your differential equation, I have to look at it, I have to debug it. So each of these 11 to 17 problems is about half an hour to 1 hour of work, right? So before the workday starts, I have 17 things that are half an hour to do. And you could see why the first 12 hours of the morning was answering everyone's questions, and then the 8-hour workday starts, right? So it's open source keeps you captive. And I think if anyone else is a open source maintainer, you've probably started to learn this. Like, Samuel Peyton Jones, he just was talking about, the cost of success in a programming language, right? This is the cost of success. The moment you have users, you are captive to those users, right? And the real question is, how do we make sure that we can solve this influx of issues so that way we can actually start working on something interesting? Because all of this, I want to respond to you every single day, but this has to, this is not an insignificant amount of work to do in the morning, right? But then the real thing that's going on is that, you just say, how do I actually get work done? First, let's try to define what is getting work done, right? And getting work done is getting an answer out to somebody, and it's merging a pull request. Now, I know that, it's really fun to work on a partial project and throw it away and everything, but if you consider, the only things that actually change the source code of the package are the things that actually have a test and get merged into the package, then if you're to try to optimize your workflow, what you do is you just say, I'm going to stop doing anything except trying to get pull requests merged. And if you look at something like the Julia library, the SciML repositories, right, there's like 10,000 pull requests that are already open on these repositories. So if you actually want to be efficient, you never write a piece of code and just go to all those pull requests and just say, which of these need to be merged? Let me merge these. And the ones that haven't been merged, let me just give a comment to you and just say, hey, look, you need to change this, 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 and this, and come back to it, right? There's literally enough pull requests already out there in the ecosystem that you can continually do that even before AI agents. But now with AI agents, you do exactly that workflow, and the person who's on the other side of that pull request goes and makes those changes and comes back to you instantly because you can force them to. That's an agent, right? And so, this is always the real productive way to work has always been to just work through looking at pull requests. It's just now we're kind of productionizing that, right? And then if you look at where all these pull requests are, you can actually see that a good 75% of them are things like very small bug reports, simple new feature requests, version bumps, right? Basically saying like, hey, someone updated this dependency over here, so you have to update this dependency over here. Hey, just change the number on your dependency because I need your package to be able to support this, even if there's no breaking changes that are involved, right? Literally 24% of pull requests that are going on are just changing version things. Or you just have to look at it and just say, hey, did they actually change anything about my code? No, my test still passed. Okay, let's merge this, right? And so, what we're able to start doing is we're able to say, hey, look, being able to find out whether we're missing a doc string on something, or be able to just bump a version dependency. What we're able to find is that a lot of these agents are just doing very simple things, like double check whether this library changed any functions that we're actually using, and if it didn't change any functions that we're actually using, then let's just accept the version number change. Well, first run test, then accept the version number change, and boom, this is now 1/4 of the work that we were doing before is then gone because of that agent. And you can say, oh, agents aren't very smart. Well, at least I think we can all agree that an agent is smart enough to do that. Just look at code that changed, compare it to the code that's over here, and say, is there anything that's overlapping, right? And it turns out that about 75% of the human originated volume is in the category of things that are sufficiently easy to be handled by AI agents. So is there something still for humans to do? Yes, we just start to get to do the actual deep design and actually interesting stuff because we get past the whole, 12 to 14, 17 issues that are showing up every single morning, right? Now, what does this look like? Well, here's a brain dead obvious one. So here's a pull request that came in, right? Now, here's how fast we scroll through the pull request. Do you guys all see what happened there? Yeah, obviously, it's very clear what to do. It only takes about 5 seconds to be able to realize that the issue with this pull request is it's not handling everything that's required for GPUs, right? Now, I say that that's obvious because I've been working on this for 10 years. And this is a point about agents. If you haven't been working on the code for a very long time, it might not be obvious. But what you can do if you've been working on something and you know the code base really well, you can look at this and say, well, you saw the way that they're doing the loop at the top, right? The loop at the top right there at line, the loop at, this piece right here, we just changed C0 partials in another piece of code, and so we need to make sure that we change the downstream library, And so, this is the one I was mentioning. So, yeah, so basically when you start to do this, you basically can start to review code where you say, hey, look, I know this code base so well that after about 10 seconds of scrolling through, I can look at this and say, well, they didn't do the fusing the right-hand side in the way that it's supposed to, but, if I was to sit down and actually want to do this fusing, I could spend the 20 minutes doing this, but what's wrong in this pull request is it takes about 5 to 10 seconds in order for me to identify and be able to change, right? Now, there's a few things that you can do. You could either comment on that pull request telling the author, hey, change this. You can go hire someone to go finish all these PRs that you don't want to merge, right? Or you can send a really quick prompt to an agent to say, hey, look, most of the code's already there. Just do this really quick change, right? And so this, for example, is what one of these prompts would look like. This is the one that solved that other one. I say, hey, rebase that pull request because it needed to get a rebase. But what you just wrote there, right, very, very obviously, like that code right there, that's supposed to be a GEM-V calculation, right? You wrote out a GEM-V calculation, so why not actually make that be a GEM-V calculation that now will make it GPU compatible, right? Boom, and now just make sure that you do an alloc check and also make sure you do a JL arrays test so that way the code is GPU compatible. That's it, right? That pull request is sitting there for about 1.5 years because no one wanted to rewrite it as a GEM-V calculation, but it takes about 5 seconds to look at that and go, just finish it, and then boom, the pull request was just done by Fable in about 20 seconds, and we click the merge button, right? Now, the one thing that I really want to highlight is I am being very, flippant about the word obvious, right? This is obvious if you've been working on the library for 10 years. I mean, you've been working on these kinds of problems, right? But what I'm saying is getting the knowledge of the code base is the thing that is difficult, not necessarily the mechanical thing of actually writing the code to be GPU compatible. It's knowing how you need to change the code, but knowing how to change the code is something that you can turn into a prompt that is very easily executable, right? Also, a big thing is coming up with MWEs, right? A lot of people will come to the SciML libraries and say, hey, look, I have this issue. And I go, that's not an issue for me. That's actually an issue for Enzyme. And the Enzyme people will go, well, but there's so much SciML code inside of here. I don't want to work on this issue. And everyone stops working on this issue, right? Well, what you can do is you can say, hey, look, this issue right here, SciML sensitivity, make a version of that doesn't call any SciML code. The way to do that is take all the code that you're going to call, inline it all into a file, and then select it, continually delete one line at a time until you have a version of that issue that has none of my code in there. Now send it over to the Enzyme folks. And they go, oh, this is a great issue. We literally had to do this by hand. This is something, this is probably about half the time I would be doing before. Now all of this is completely agentic, right? And so you say, agents can't do everything. I agree with you. But that is something that would take an hour to do that is now completely automated, right? The big question is, okay, we start to do this. Did quality decrease at all, right? And if we look at what actually happened, I think that the big headline figure here is, how many PRs did we actually have to do a follow-up pull request to because after we did the pull request, we accidentally gave you an extra bug, right? With agents, it's 6.36% of the time. Before agents, it was 6.41% of the time, which means, is this AI slop actually introducing more errors into the SciML ecosystem? It turns out that it is actually slightly better than what we were doing before. Because again, there's so much going on in open source, and that you'll do some change. You'll be like, oh, let me make this change, and you accidentally break GPU usage way over here. Well, if you tell all the agents hey, test literally everything before you make your pull request, it actually seems to find more of these issues about things that you were not finding before. And we have the hard statistics to show this, right? That is actually not introducing AI slop. It is actually improving the code base without reducing the accuracy, right? And in fact, after people started to see things like, the agent will make a change, and it also will do very comprehensive benchmarking and found, but if you merge this, you get this performance regression. We started having some people say, hey, can you make your agent also look at my code base and make sure none of my PRs are doing performance regressions? Because when I do human changes, I accidentally, forget to measure performance and things all the time because I don't have the time to do all that, right? With the agent, you can force it to do all these extra checks that you never wish to do yourself, right? And have users actually been able to notice a difference? It turns out that our average response time for going from an issue to a pull request, on average, or the median, has gone from about 25 days to 4.3 days. Again, all of these statistics we calculated all of them from the repository. I can show you all the code that was done to be able to calculate this. We've actually decreased by about 20 days our median time to bug fix. Again, without sacrificing any accuracy or correctness in introducing AI slop by this measure of the number of pull requests that needed a follow-up to fix something because, oops, we worked too fast, right, has actually gone down. I will say that there's one thing that we've had to do with this, right? One of the ideas that we've introduced is a sacrifice repo. A sacrifice repo is a repo where we say, hey, look, this is something that's going to be probably pretty vibe coded. So let's just forget about how this code looks like, right? And so a good sacrifice repo is pure_klu.jl. This is one where he said, okay, there exists this there's a sparse matrix solver that lives in C. It is KLU. It's part of Sweet Sparse. We want a version of that because I want to change some of the algorithms in there, right? So the first thing that I told it to do is, hey, translate this from C to Julia, right? And the way that I would write this in Julia is not how you would write it in C, but the pure translation is going to give you some, some not very good translation, right? And at that point, you just say, this is a sacrifice repo. It is not a repo that I will ever want to touch. I'm never going to want to open this up in VS Code because it's never going to be, I will never spend the time to make this code base look good, but I can still work with it through an agent. I can say, hey, look, take the KLU algorithm, and now in the AMD function, one thing that they didn't do in SweetSparse is they didn't, for example, specialize it on diagonal matrices, So you can still work on that library, but we've now sacrificed it to say it is now something that a human will never want to look at, right? I would say that, we don't want to do that to all of our code, right? Most of our code base, we still want to have very human-generated and very human-driven. But in order to move at the pace that we're working on, there are some projects and some functions and some repos in there where we've basically sacrificed it to the agent gods, right? And I think that by saying that, hey, look, there's some of these where we're going to do that for, and some of these that we're going to be very much caring about every line of code. I think that by separating those two with some clean separation, it has allowed us to be able to move faster without having to without having to sacrifice everything, right? And so I think it's a good idea to have in mind that maybe some projects or some parts of projects can be sacrificed to. This is a vibe-coded part of it, but it's linear algebra. Numerical linear algebra is very easy to check for correctness, right? You basically can have, does it give, we actually have tests that is hitting exactly the floating point numbers as KLU, and so since it's getting exactly the floating point numbers on an LU factorization, we can be very sure about its correctness, even though no one will want to be going through that code. So we've sacrificed that repo, but we're still moving forward with it, right? What was the infrastructure that was built to make this possible? So the way that I do this is I have an HPC node set up at MIT. This is called AMDCI2. You can see my two commands, right? What I do is I do /AMDCI TMP. It opens up a new tmux window, and then what I do is I either do Claude skip or codex skip. This opens up a version of Claude or codex with full permissions. It's allowed to do anything. It's allowed to modify anything on that computer. But since it's not my computer with all my credit cards and everything, I'm okay with that, right? And I basically just keep a whole bunch of those agents running on that computer, all in different tmux windows. And because it's tmux, I can go in a new SSH session from a new computer and then keep on tabbing through. You can even see right here. Here's all the different tabs, of a bunch of different agents. And they're just all continually running. They're all continually running on this one computer with 128 threads. And now the key thing here is that I can then go to my phone. In fact, this is the screenshots from my phone. If you do /RC, turn on remote control mode, all of those agents are also there on your phone. And so, I can prompt all the agents. I can write out, these very long paragraphs and say, here's all the things you need to do. And as I walk up the stairs, I just start to go, okay, which one's a finished? Oh, this one finished. Let me look at the code. Oh, you didn't do this right. And now I can send really small responses from my phone to be able to tell it to update things. When I get back to my computer, boom, I go back and I just write the bigger prompts again, right? And so basically, we just have a system that's just continually running tons and tons and tons of agents, and we have multiple different devices that can all jump into it, right? That's how you can work from the beach, and then you also go back to your desktop and then type out a bit more, right? And it's really a huge change, right? And another huge thing is to use goals, right? So for example, we've been doing a complete sweep through and making all of our doc strings be completely uniform. You can see what we say is, hey, look, we wrote an entire syntax statement of, here's SciML style. This is how we want all of our documentation to work. Go through every single SciML repository and keep on making pull requests until all of our documentation matches this style. It's been now working on doing this for the last month and a half. It's opened up 444 pull requests to be able to review, and it just keeps on going. It probably has about 2 weeks left. And again, all I have to do in order to finish these things is you look at your phone, you look at your pull request, and go, okay, there's another thing done, another thing done, another thing done, right? And it's continually just making the code better and better and better. Now, I think I want to end on one last point. Should you change your workflows to this, right? When I'm saying that, when I'm saying that, oh, this is easy, like it's very easy to look at that code and in 10 seconds know how to prompt it, right? That has become from the fact that I've been working on this code base. I've been doing this for about 10 years, right? If you have not learned how to program well, if you have not learned about all these things for performance and everything, then you're not going to learn anything from this. You need to be able to look at the code and instantly know, oh, this code will not be GPU compatible. Let me tell this, If you have not understood programming well enough for this to be instant, then it's probably not a good idea for you to start using these tools, because if you don't start to learn it, then you're going to keep on running into the same issues over and over and over. And so I think it really is causing an issue with training new folks, but if you're already trained, then I think it's a very good accelerator. I do want to end on one last point, but is it fun, right? And I will say a lot of people think about the programming as something that is fun. They really like playing with it and really like typing and everything, right? The statement that I've made here is, hey, I've changed everything that I'm doing with programming from playing around with programming to now all of it is reading emails and responding to emails. And was responding to emails the most fun part of your job? Probably not, right? But it is more efficient. So, is that a trade-off that you want to do? Well, I would say that, for example, taking a piece of code and then making it GPU compatible or making it non-allocating. I mean, the first 100 times I did that was probably interesting. Now looking at someone's code and being like, oh, it's allocating, let me rewrite your code because you did this wrong, right? I've done that a few hundred million times. I think I can tell an agent to do that and not feel like I've lost anything. But if I did not do that 100 times before telling the agent to do it, then I will have lost something. So, is it fun? I don't know if this is actually the most fun way to work, but it is actually very efficient because now everything is just in emails, right? So hopefully that's kind of a quick overview of how we're doing this, right? I'm showing you, here's some prompts, here's our system, here's everything. And I think the statistics show that this has been beneficial to SciML. But, whether or not you should adopt it, it really comes down to, do you think that this kind of workflow is I think that you can say that this workflow is useful, but I also won't say that this is the most fun workflow. So maybe I'll end it there. So thank you very much.
Okay, we have time for questions. You point out when you want questions.
Yeah.
A very nice talk. I guess one question I had was if when you prompt these agents, you add extra tests, right? Has the time for CI kind of increased as you kind of use more and more agents? Maybe there's overlaps in tests?
That is a very good question. Yeah. So in fact, the amount of our CI has increased a ton since because one of the things that came out also last year was Julia's new trim functionality, right, for building small binaries. So basically, we did a goal where we just said, okay, /goal, make it so that way all major functions that are used in the SciML documentation are trim compatible, right? And then also add allocation checking everywhere, and also make sure all these functions are GPU compatible, right? Basically all these things about you need to make sure all your interfaces are correct. This is a big issue that we've had in SciML for a while. I know that we have interfaces somewhat defined, but now how do we make sure that we make that every single type that should work in SciML always works, right? We basically started to do a bunch of goals where we just said, let's take every single array type and every single number type and put them all into our test system and fix any issues that this comes up with. It is a very routine, easy thing to fix, right? So for example, if one function isn't working with GPUs, then someone probably did a scalar indexing. You just need to turn that into a broadcast operation, right? It's a very easy change for someone who's been working in Julia for a long time, right? But there's hundreds and hundreds of those mechanical changes to do, and then after you make that change, you need to turn it into a test. So actually, we've seen our test times explode. I think for ordinary diffEQ, the full test time actually takes around 18 hours to run the entire test suite now. We parallelize it over I think 92 jobs at this point, and so it runs in 20 minutes in terms of human time, but that's because it's parallelizing a lot, right? We actually had to buy 2 new HPC nodes and plug them into our system just to be able to have enough CI machines to be able to continue to run this. So this has completely ballooned the amount of time that's running on CI. I mean, in fact, we're running way more on CI than we ever did before because now we basically do these changes and then we let the agent throw things up there and we don't even look at the code until it's already gone through CI tests, right? And so we're relying on continuous integration. So this is expensive on compute, but because of that, I can now, because we're relying so much on tests, we're just overloading all the tests for the reason of I want to be able to trust the code even if I don't pull it and run it myself. And that's the sacrifice that we're then going to do. Then we're going to pay a lot in terms of automated testing. Yeah.
Can I just ask the next speaker to go down and set their computer up, please? And do we have any more questions?
Thank you so much. It's very comforting and orienting to hear that a very similar process has been happening, not only that I use in my libraries, has been also happening in general. I'm a cognitive scientist. I'm researching attention. I'm actually curious about the process. I have felt in myself the split or the fragmentation of my attention. How is it for you? Have you noticed any changes in your workflows and in your own cognitive states when working?
I think that that is a very good question, right? Because people kind of have this thing of I think there's some fear going around of if you use AI, it's going to change your brain and you're going to lose everything, right? it feels like TikTok, right? But if the way that I was working before is I'd only spend about 3 minutes on every single pull request, throw the code out there, and go on to the next one. So instead of having 8 of those going on, now you got 40, you got 80 of them going on, right? So it really the context switching already was a part of the system that I had before. It's not too different. But also the thing that I want to actually highlight is the reason why I had to do so much of this context switching is because so many of these pull requests were bumping versions and doing little like a typo fix, right? And again, what's actually happened is about 75% of the pull requests, those trivial things, are now gone. And so what I do is I just prompt everything out, I get everything going, and then I actually have 2 hours to myself to actually work on an actually interesting hard problem. In fact, we had so much going on in the open source that was just simple things that I didn't actually get to work on any hard problems. So has my brain rotted because of AI? No, I actually get to actually work on math now, because before I was literally just bumping versions for months and months at a time. So I think that's a great question, because people always think your brain's going to go to slop. We have proven, I think, that this is the exact opposite. So thank you very much.
All right. Thank you, Chris. And our next speaker. Do you want to introduce yourself? Okay. Oh, sorry. Do you want to introduce yourself, or do you want me to give you a short intro? Introduce yourself, and let's get going. Can't sorry for that.
Start now? Okay. Can you hear me? Okay. Good morning, everybody. I'm Jacob Quinn. I'm going to be talking about Agentif, also on the kind of AI track of things. That was a great talk. Chris, he's amazing. We all bow down and, hope to be as energetic as he is. I want to talk today about some of my own kind of dabbling and playing around with some AI stuff in Julia. It's also been a lot of fun as an open source contributor to kind of see the advancements here, try to find the ways to efficiently kind of leverage these new tools. And today I want to kind of focus on what we can do in actual Julia with some AI primitives. So there's a couple different building blocks here that I'm going to talk about. The core of the package is called Agentif. It's a whole suite of packages that's in one repo in my personal organization. But the Agentif is where we actually define like an agent kind of core, which is really just a system prompt and a set of tools that it has access to. And then some kind of model provider, some kind of API that we have access to. And then that agent, you can then evaluate things. You can give it a prompt, and it'll go evaluate, call the LLM, call tools, and kind of do its core agent loop there. So at the very base of things, this harness is actually a very simple kind of program. It's really exciting, though, once you start looking at all the other pieces that kind of fit together. So at the core of it, we're obviously interacting with model providers. So here we have, OpenAI, we have Anthropic, Claude, we have OpenRouter, which provides access to tons of models. You also can run models locally on your computer, right? So these are locally running models. They all expose kind of a fixed set of APIs that you have to interact with. So you're at the very core of it, you're making an HTTP request to their API. Even locally, when you're running it through Llama CPP or Ollama, they're exposing like an HTTP interface. You're making an HTTP request, and then you're basically getting a streaming response back. So it's called SSE, server sent events, where it's basically a long streaming response, and they're just emitting these kind of little data packets as the response streams back. So everything else is kind of layers on top of that. And so when I started playing around with this. I dug into some of these kind of agent harnesses, especially the ones that were open source. One of the biggest, I would say, is a project called Pi. It powers the kind of Pi coding harness, but at its core, it also is just like an open source agent at the base. And so that was really fun to kind of dig into, see how actually simple it was kind of at the core, and then start to kind of play with my own ideas around what that would look like in Julia. And I'm going to switch over to some actual code here. So this is actually the Agenty package. I think that's big enough. But I just kind of wanted to show how simple this actually can look. This is kind of the core kind of tool agent calling loop. And so you always start with an agent. And this is all structured around a middleware kind of set of layers. So this tool call is just one more middleware, okay, that gets inserted into the stack that makes an agent, okay? There's also, middlewares around session compaction, session storage. You can do fancier things like queuing messages that will get evaluated next, or steering, okay, where you're actually injecting a prompt in between tool calls, okay? So these kind of all factor together. But even in this tool call middleware, okay, it's really simple. We have a while loop, okay? We are submitting to the next layer in the middleware stack, which at the bottom, like I said, is this kind of stream function. We're sending the prompt to the LLM provider. We're getting that response streaming back. And then essentially, if there's no more pending tool calls, then we're done. We return. Otherwise, we kind of loop through the pending tool calls. We call them. We have a future-based thing where that's what we use to evaluate the tool calls so that we can evaluate them in parallel. But then we're essentially waiting on all those futures, and then we loop back around, okay? So we provide all the tool call results back to the model, okay, back to the LLM provider. We say, here's all the tool call results, and it starts streaming back what it wants to do next, okay? So at the core of it, that's kind of an example of like how simple these layers can be. The power is when you kind of are able to stack them all together. And so even if we look down here, this is kind of the default stack of what you get when you make an agent here. We get compaction, handling, steering. We have tool calls. We have session management, where it'll actually keep track of your session. That's really important for cache response or caching of the kind of session as you go along, so that it doesn't cost crazy amounts. We have a skills middleware where we'll actually load agent skills that are kind of globally. Those are made available to the agent, so it can pick those if it needs. And that's essentially it. And so this is kind of the default way that you can evaluate something with an agent, and you get this default stack. So it's a lot of fun. Some of the other inspirations I've looked at a little bit. There's the OpenClaw project. Chris mentioned that. It's kind of meant to be a very autonomous agent that you can kind of just set up and then interact with as like a personal assistant. It's an interesting project because it exploded so much in popularity. And the guy is even more AI pilled than Chris, which is crazy. But it's on the messier side of kind of these open source projects, in my opinion, just because it's kind of exploded, and there's a balance between, am I designing this in a simple way that is going to be, functional for a long time, versus I'm just kind of churning features and issues and things out. Another inspiration is called the Hermes agent. This is by a new research. They've also kind of taken a slightly different approach to this personal assistant idea. The Codex CLI by OpenAI is actually open source, so you can go look at that repo, dig into how they've kind of built everything. It's all Rust-based, and it's got some interesting ideas. They tend to make a very vertically integrated stack, so they're obviously calling their own API, OpenAPI's response. They made like a special WebSocket, implementation to do the streaming even more efficiently. So it's really interesting to kind of see how they've evolved their own harness to adapt to a lot of that. Let's see. Oh yeah, this was the talk, the slide about those. So part of what I wanted to do when building this in Julia was to keep it extremely simple. I think one of the power and one of the advantages of the Pi approach is how minimalistic it is, and it tries to be. It keeps the code very legible, and ultimately I think it really helps the model performance when you're doing actual agentic work, is to keep things as dead simple as possible, especially as the models get smarter. It kind of has less for them to trip up on or get in the way. So let me walk through really quickly kind of each package and kind of its purpose. So we have the LLM providers package. This one is really just a base package that provides access to a registry of models, particularly around like the open router, where it provides access to so many different models. You can kind of enumerate them, choose between them, see their different costs, the various sizes of context windows, that kind of stuff. So this is kind of a base package that's more of like a content registry for the rest of the stack. There's the LLM OAuth package. This provides the ability to use like an OAuth login through Claude or OpenAI, so that you can then leverage those subscriptions when you're doing when you're choosing a model and then hitting those APIs. It's kind of a utility package, but it helps hook into the a non like API based cost of how you're using the model. We kind of talked about Agentif a little bit. It has the core ability of evaluating, streaming, executing, and then kind of looping through those. It's the core set of middlewares. This is kind of a quick little example of how you would set up an agent. So on the right here, we have a tool. We're using the tool macro to actually define the tool here. So I have a description. I have a function that gets called, okay? So it knows, okay, I need to provide a city as a string, and then if the city is mains, I return this temperature, and if not, I return something else, okay? Very, very simple tool, okay? But then I can define my agent. I give it a system prompt, okay? Answer with tools. I give it a model definition, okay? I provide an API key, and then I provide the set of tools that it has access to, okay? And then I can just call evaluate, okay? I call evaluate with the agent. Hey, what's the temperature in mains? The model, okay, will then get that initial prompt, temperature in mains. It says, okay, what tools do I have to answer this question to kind of do what the user's asking me to do? Oh, I have a tool called, return C, okay, for the temperature. I'm gonna call that, I get 28 back, and then it'll provide that response back to me as the user, okay? Very, very simple example, but it's really as simple as that. As we talk a little bit more, there's another package called LLM tools, okay? And this is where we're kind of trying to provide a really useful set of tools that are generally really useful for agents to then do work with, okay? We have file tools, so being able to read, write, edit, list, grep, find on files. We have web tools where you can fetch pages and search the web. We have PTY sessions, okay? This is interesting because it's different than just like in Julia running a command kind of sub-process and getting the result back. Opening a PTY session actually is like opening a full terminal for the agent, okay? Where it can write things to the terminal, things get evaluated, things can run. It can run its own Python kind of, REPL if it wanted. And then it can close that when it deems that it's done. So it's a bit of a different tool than kind of a one-shot kind of bash command. Its ability for it to kind of open a terminal, work through that for a while, and then close it when it's done. There's also kind of delegation where this is like a sub-agent tool. Also similar is like the Julia workers. So the Julia worker is where I'm actually spawning a separate Julia worker process, and then we're communicating with that over TCP. And it's an ability to kind of, if you know like the distributed standard lib, it's very similar to that. It's kind of a much simpler and, in my opinion, better implementation for same machine kind of IPC and kind of remote execution. And then sub-agents is very similar, but instead of just spawning a Julia process and then kind of evaluating Julia, we're spawning a sub-agent, okay? So agentif is loaded, and we're defining some kind of agent with a system prompt, and then giving it a prompt to evaluate, okay? So very similar. They share a lot of the same kind of infrastructure, kind of a sub-Julia process and a sub-agent, just slightly different purposes. And that's kind of what we talked about here. You can load these tools from the LLM tools package and then provide them to your agent. There's also a claw package. So this is kind of my take on like the personal assistant type setup. So in this example, it uses a single SQLite database to kind of store all of its state. It has an event-triggered setup. So everything that the personal assistant evaluates is based on some kind of event that gets triggered. There's actually a REPL interface to the claw agent. So you can start in the REPL, in a Julia REPL, and you can go into kind of claw mode, where you're talking, everything you type at the REPL gets sent to the personal assistant as an event to evaluate the text that you provided, and then it'll respond in the REPL. And there's a lot of other integrations there. If you want to load like the Slack extension, there's a Microsoft Teams, there's a Gmail, there's, you know, all of these kind of normal personal assistant interfaces. These are extension packages. So it's just a matter of saying, you actually talk with your assistant, and you say, hey, I would like to turn on this, you know, integration. Okay, give me the config, give me the API key, whatever it is, and then it'll set that up as a trigger. So I like that approach. You can set up like a GitHub integration. If you set up a GitHub app and provide it to your assistant, it can actually then, you know, get every event that gets triggered based on how you've configured it, and it'll evaluate based on whatever comes in. So in terms of, that's a slightly different approach than some kind of assistant setups where it's, you know, relying on some kind of heartbeat scheduled cadence thing. It just wakes up every minute and tries to find something to do, or checks some kind of message log and responds to things. And then, you know, usually they have some kind of direct chat, you know, back and forth. This is all pure event driven. So everything comes in as event, and it'll respond based on the events that come in. And then the other thing I've been playing around with more recently is actually a minimal coding agent. So I called it JuCo. It's kind of the Julia coding agent. It's meant to be extremely minimal. It only has 4 tools. So I have a one-shot bash tool. I have a read, an edit, and then a remember. So it has some ability to kind of remember things it learns as it you know, works through things. So got to do a quick demo, right? So I can actually load up the JuCo REPL here. So this is my little agent, and then, you know, I'm in the agentif directory. I can say, tell me how many lines of code is in the core agent loop in agentif, okay? We'll give it a simple question, and it can kind of go down here and try to figure that out. I'll bump this out so it's bigger. This is based on just an open router DeepSeek model with reasoning turned on. So you see it has the thinking kind of comes on, and we'll see a little bit of, you know, what it's doing here with the tool calls. And then some of the things it's working through. But really, this is all based on the pure kind of Julia stack here, okay? So that's really all these coding agent harnesses are. You have the core kind of agent harness. You're giving it a certain number of tools, okay, that allow it to read and edit and do coding tasks, right? And then It's just a matter of prompting it and kind of letting it go to work. So what kind of progress is it making? Is it kind of looping around here? Agent doesn't seem to have a main loop. Let me look at session. Oh, it looks like it's having a hard time finding it. That's okay. A lot of the time it's based on the tasks you're working with, it matters kind of the exact model and, the level of reasoning that you give it. So, that's a lesson where these frontier models, there's a reason they're very expensive. They are very good. They are very much more efficient reasoning-wise, and so they can be much more efficient in their tool calling and kind of getting tasks done versus, some of these other dumber models, so to speak, that might, churn and churn and churn and waste a lot of tool calls, waste a lot of tokens, okay? So it finally found it, okay? So the core agent loop is the wild true in the tool call middleware. So good job, little agent, you did it. So that's, and then it'll kind of show us some stats here, right? How long that took, how many tools it called, how many tokens were used, and we get a little example of like how much that cost. So it was 0.003 cents. And how much of our context space is used, only 1% here. The last thing I want to talk about is how we're kind of leveraging this at Ondavo. So here's my shirt. That's where I work, full-time job. We're building a tech platform for corporate travel, kind of from scratch. So being able to book your flights, manage your trips, do everything through a mobile app or on the web. It's actually an interesting problem and an industry that's kind of very behind tech-wise. So it's been exciting to bring some of this forward in the industry. We use this stack in a couple of ways. We have a core set of tool definitions. So being able to search for flights, search for hotels, look up your past trips and your past preferences, travel preferences. These are all core tool definitions that we define using agentif tools, okay? And then we use those tool definitions, so those are actual abilities you have in our product to then power two different kind of entry points into that. We have an MCP server, so you can actually go into Claude and, if you're an Ondavo customer, you can add the Ondavo connector in Claude. You then authenticate with your Ondavo login, and it then knows who you are as a traveler in our system. You can say, hey, what's my trip? What hotel am I staying at next week on my trip to, Germany? Can you help me book a trip to New York in a couple months, okay? Those kind of things. And the MCP server is really just providing Claude basically access to the Ondavo tools, okay? We also have an in-product AI chat harness. So when you're in the product, when you're on our mobile app, when you're in the web, we have a native AI chat interface where you can then pop that up and very similar, start chatting with it. Hey, can you help me look at this? Can you help me figure out this bug on this page? And it's using the same core set of tool definitions. So we love having the control over the harness. We love having the ability to build kind of our own AI stack in this modular way, but allows us to kind of define the core set of tool definitions, and then we can kind of build everything on top of that. But that's kind of everything I talked about today, and let me know if you have any questions. Yeah.
So when you write a tool description using the add tool macro that you have, do you parse the arguments, the types of arguments to give it to the LLM? Do you parse it by the method definition, or the user has to write it?
Yeah, it'll parse those automatically, like the function name, the arguments, and it kind of provides that. What I've noticed is you tend to need to spell it out even a little bit more for most models, just so that it's very clear what each argument means, what it can and can't provide, that kind of thing.
And one more question is, so the agentif, you only support React loops, or you can add a custom node if you want to? Like, if between model tool call and should continue, like it's a loop, right? So if I want to add another node, is that possible?
Yeah, completely. So like I showed down here, the default evaluate function is building this default handler stack, okay? So that's just saying that here's the set of middlewares that I'm going to stack together that all get kind of layered together for the default evaluate. You can completely come in, pick and choose which layers you want, define your own tool call middleware, and kind of compose it however you want. Yeah.
Any more questions?
Yeah, right here.
Keep your hand up.
Just a quick one. You said that you support local LLMs. Like, do you have specifics about the like hook-ins that you like to use? So like Olama or VLLM.
I haven't had a chance to play around them a ton. I've usually just used Llama CPP to run. I have access at work to a much larger machine, 128 gigs that. With some actual GPUs that can actually run some of the like non-trivial models. Mm-hmm. Those can actually be pretty efficient. You can get them up to kind of 50 to 80 tokens a second. And the latest models, some of these DeepSeek models are actually pretty decent. So I think it's getting there where it could actually be a viable option for like simpler tasks. But usually these programs, the Olama, the Llama CPP, are providing the same kind of like OpenAI chat completions API that we hook into at the base.
Okay, sounds good. Thanks.
Yeah, right here.
Hi. Can you show an example of how you actually spin up the MCP server and what is the scope for, say, deploying this on an Azure virtual machine or on the AWS? Because I think you're just doing this locally currently.
Yeah. So you can definitely run it locally with the MCP server. Ours for Ondavo is hosted. I actually have a package called Model Context Protocol that I've been working on. I think there's already one that's publicly registered, so this is slightly different. I haven't had a chance to go kind of compare, whatnot, how they work together. This one that I built is based on kind of the Agentif stack, so it integrates directly with some of the tool call definitions. So if you define a tool in Agentif, then that can directly translate into an MCP tool definition. But then it's really just running an HTTP server that exposes the right MCP protocol, and it also supports the authentication side. So there's a new OAuth package that I've helped develop. It uses that to do the right kind of OAuth dance to authenticate the users. So once you have that all set up, it's just a matter of hosting that anywhere you want, and then users can directly connect to that.
For example, if you're using Azure functions on the consumption tier, it limits like the response time you can have between like a question and an answer. In this case, is it just any generic HTTPS capable server will do? Are there limitations on what you can deploy to or cannot deploy to?
Yeah, I think you just have to structure it in a way that's efficient, right? So if you have a tool call that ends up taking a long time, that's probably a good example where you need to split that up, right? You would split it up into multiple tool calls where I'm kicking off some kind of evaluation. I have another tool call that can kind of pull for the result, right? You do have to keep each tool call to be kind of a reasonable execution time.
Okay, we have time for a couple more questions. Right at the back.
Way in the back.
Getting my steps in today.
Yeah, great presentation. I was curious if you've had the chance to benchmark the JuCo agent against any of the other coding harnesses, especially on like a Julia task.
Very little. It's still very much kind of a toy, something to play around with. I do really like the idea of kind of a very minimalistic coding harness. I think the way that the models are going in terms of their advancement and their pre-training, they know kind of how to do tasks very efficiently if you give them a very small set of tools and just the flexibility to kind of operate how they want to. So I think there is some value in it. Is it an industry grade thing? No, not by any means. But I think it is fun to play around with. I think Julia does provide some interesting advantages, so to speak, in terms of being able to very easily, it's like a one-line thing to say, I'm actually going to multi-thread, execute tools in parallel. There's other coding harnesses that can't do that, or that have a very much more complicated setup to try to do things like that, or to do kind of the sub-agent architecture, or to spawn kind of a sub-Julia process. All of these were very, very simple tool definitions in Julia because it makes a lot of those kind of abilities, those tools, very easy to do. And so I think that's probably the area where you could get the biggest advantage, just because that's a lot easier in Julia than other languages.
Okay, we have time for one more short question.
One more question.
So you mentioned you use this for like a travel booking type application. So most of the sessions yesterday relates to like scientific computing, HPC. So I'm just curious, what are you getting out of Julia for this particular like very retail-facing type of application? Like, because most people would do that in React, Python, Java.
Yeah, we use Julia for another key part of our stack at Ondavo. So we do flight event processing. So every flight in the world that's currently active, there's usually some kind of 100,000, 110,000 a day. We hook into a fire hose of data that's coming in. It's one flight event every 1 to 3 milliseconds. And we process that all in Julia. And that's a great task for Julia. It's very efficient. You can do the JSON parsing and the state management and the kind of threading management of everything very efficiently. And so because we were leveraging for that already, when we started exploring this kind of AI integration, there's a lot of messy kind of code bases out there that you can use. We currently use Java and Julia on our backend. And so it was a question between, can we do something in one of those two? And Julia is a great fit. It's like you saw, we can build kind of a simple agent harness in Julia that's very understandable, very legible, very easy to maintain. And then we can kind of build on top of that with whatever we need. So that's kind of how we came to the decision to use Julia.
Okay, thank you very much. The next talk here is at 11:15.
Okay. Welcome, everybody. Hello. Thanks. Hi. I'm Philip. I guess I'm the first speaker in the session. So I'm going to talk today about gradients aren't always great, a case study with Mixed Models JL. I'm one of the core developers of Mixed Models JL for the last couple of years, along with Doug Bates. And so a little bit more history about where Mixed Models JL comes from. It is kind of the conclusion or the latest step in a research program that started in the 90s that Doug Bates was working on. NLME and R use generalized least squares, and this is still the standard in most other software packages that use mixed models. In the early 2000s, Doug, along with Martin Meckler and Ben Bolker, worked on LME4, which was really a massive change for the field, especially for my own field, where we have two different types of repeated measures. We have both subjects and items, and this allowed cross effects. But the important thing is that they changed the problem. So they were no longer doing this as a generalized least squares problem. They're using penalized least squares. And that's relevant because it means that you get a sparse matrix formulation of the problem. And so they used general sparse matrix methods, and they did this in R and C++ and Eigen, and it is a delightful package, very important piece of software, but it is hell to maintain. And I think even the current maintainers would agree with that statement. You're bouncing back and forth across the language boundary all the time. In the 2010s, Doug retired and decided the best thing to do in retirement was to learn a whole new language and just live life to its fullest. I'm quite envious. And so he worked on Mixed Models JL, and I joined the party in 2019. We still use penalized least squares here, but we take advantage of Julia rather extensively, and we have specialized sparse matrix methods because we don't just have sparsity, we have particular sparsity patterns. And so Julia's type system and multiple dispatch really allows us to have very, very specialized methods for particular types of sparsity. Most of the methods are in place, and we allocate almost nothing during just a few bytes. Not kilobytes, bytes, when we fit even large and complex models. And in 2026, and this is the relevant bit for today, after repeated attempts by Doug and myself, we finally got an acceptably fast evaluation of the gradient of the objective function in Mixed Models JL. We have been jousting at this windmill for many years now. So you might be asking, why is the gradient so hard? And people have been asking this for a long time. We get lots of questions about why don't we use gradient-based optimization? Or somebody, Andreas Nowak, actually did this and wrote an allocated version. And why didn't we use autodiff? Well, because it didn't really work for the heavily optimized in-place algorithms we had. And when you started doing it out of place, it gets a lot slower. And you start allocating a lot more memory, and it just is really messy. And forward diff is sadly very good, but not magical. And so, what about an analytic gradient? Well, this is, I want to call it something we have at our Beacon Slack, which is that our emoji for just is a red flag. We have been working on this for quite a while now. Doug, especially every year or so, gets really motivated to try to make this work. And we never quite got it to work. We got pretty close earlier this year, and then I had a couple of weeks access to Fable, and with that and a lot of iteration, we actually got it over the threshold. And so testing setup, this was done on a first generation Apple Silicon MacBook, and gonna work through these graphs quite quickly so there's time for questions. One thing is that the evaluation time here, you'll notice for the objective is quite low, so this is the green cross, and the analytic gradient is the yellow triangle, the forward diff-based gradient is the blue circle, and you notice that evaluating the gradient takes substantially longer than evaluating the objective function in all cases. Likewise, for memory, you see that evaluating the memory, as I said, is less than 10 to the 0, so less than 1 kilobyte in all cases for the objective function across a range of models of size and complexity, while evaluating either gradient takes a lot more memory. And then that's in addition, those are allocations in addition to the actual workspaces we pre-allocate for the gradients, which are quite large. And you can see for this one model, right, this is more than 1 gigabyte that's allocated for the gradient workspace in addition to everything else that we're doing. So the question is, but if we're using a gradient-based optimizer, does it work? The blue circle and yellow triangle are the number of iterations to converge to the optimum versus for our gradient-based methods, while the green cross and mauve rectangle or square are using a gradient-free algorithm. And you can see that you take a lot, sometimes 100 times or 1,000 times fewer iterations to converge when you're using gradients. So you'd think the gradients would be a net win until you look at the time per iteration and you see the story is reversed, where using the gradient takes often 1,000 times more to actually get per iteration. And so if you look at the total time to fit, you can see it's a wash for most of these models, right? So for example, near the penicillin model, all the values are stacked up on top of each other. Out in the right-hand side, there are some models where we start to see performance benefits for these very complex things, but you see that's not a clear story, right? So the MRK17 model does very well using the gradients, but even the next model over, there's not as much benefit. And so this is really highlighting that even with this newest, fanciest version of the gradient that we have, we're not quite seeing the same wins that we'd hoped for. Why do we do so well without the gradient? And I think this is like kind of the take-home message for people who aren't us, is like, when might the gradient be useful to you? And one thing is that we have very low time and memory cost per iteration. Our objective function is extremely efficient. We use extremely specialized matrix types and linear algebra methods, taking full advantage of the particular sparsity patterns that occur in the PLS problem we're trying to solve. This is really, again, Julia conference, I can't emphasize enough how much multiple dispatch makes this great. Even indexing is heavily optimized. We recently rewrote some of our indexing so that we're actually computing some of the indices ourselves rather than relying on the multiplication methods provided by some packages. And we do this, and which is incredibly specialized. We also sort entries during model construction so that we get very dense blocks and then huge swaths of sparsity. And again, we use in-place methods, and so this makes that we have low time and memory per iteration. We also have very fast convergence. So the two optimizers that we use most commonly are Bobbyqua and Nuwa, and they both use a quadratic approximation to determine their next step. And the objective surface that we're looking at is approximately quadratic, and when all assumptions are fully met and the data is perfectly balanced, it's actually exactly quadratic. So in a quadratic approximation to a quadratic does very well. Not surprising at all, I think. So we do very well with just using box constraint optimizers. Why is the gradient so comparatively slow? To the best of our ability, we cannot find a way to cut the allocations any further in the gradients. You're welcome to take a look at the PRs we have open, please do, and try to help us cut allocations. But the other thing is that we lose many of the nice numerical properties of the original problem. So we need these large workspaces, or we need an allocating version of the gradient, or of the objective function. And the other thing is that we lose the sparsity patterns that we gain so much performance from. And this ties into another thing that we get asked a lot about is, what happens if we use GPUs? And the answer is nothing. We get no benefits because our speed comes from these very specialized sparse methods, and those don't work so well on GPUs. Right after I proposed this talk, Stephen Johnson commented on a different discourse question, where somebody's asking about using derivative-free optimization for a problem because they're having a hard time figuring out how to write their gradient, even using autodiff. And the key element for me here is gradients only become indispensable when you have thousands to millions or more parameters, as in topology optimization. For mixed effects models, a model with 100 parameters is rare and almost always a bad model. So that's part of our secret. It's also part of the secret of our optimization, is that the PLS formulation of the problem actually profiles out many of the parameters that other GLS type methods would have. And so we have fewer parameters to optimize over. And that's it. I have time for questions. I can show any figures you want to see. Again, I went through this very fast, but thank you for your attention.
Okay, questions?
Hi, thanks for the gradient rant. I was wondering, did you give a try to any mutation-friendly autodiff backends like Enzyme or Mooncake? I have not yet. And this is partly just a matter of time on my end. Contributions are welcome. Forward diff is just the one that I have actually worked with and is familiar with.
So you mentioned that the forward diff versions of your functions need to be allocating. Have you tried using pre-allocation tools.jl?
We have not used pre-allocation tools. I have looked at some of there was another discourse post recently on a slab allocator and these kind of pre-allocation things. I have looked at that. I have not toyed with it yet. So this is workspace memory. We did do a lot of rewrites to take advantage of the gradient workspace as much as possible, but we have not tried to take advantage of any manually managed pools or something like that.
Gotcha. Any more questions? Also, can I prompt the next speaker to go and set their computer up? Do we have any more questions? Oh, yeah, no, one more question.
Yeah, thanks for the talk. As someone who has also, taken stabs at optimizing things multiple times over years and given up, and you mentioned that you finally pushed it over the line. So maybe this is a bit more of a meta question, but what did it mean for your project to push it over the line? Let's say.
So there's a particular subset of models that this actually helps. And so for those models, we actually saw performance increase. Previously, when we compared the different attempts we had, we never actually saw a net performance increase. We would get things working, and there are other uses for being able to evaluate the gradient and mixed models. So there's certain convergence tests you can do. There's certain additional quantities you compute if you have a gradient. But it was never the net performance was always much worse, both in time and memory. And so we finally got it so that for at least a very small subset of models, things work better. So.
Okay, thank you very much.
Thank you. Sure. Hi, everyone. My name is Timon Hinrichs, and today I will be giving a talk about our program synthesis library under the wonderful name of HerbJL, named after Herbert Simon, one of the founding fathers of the field. And I gave this talk in multiple venues, and today it's going to have the subtitle of Program Synthesis for Everyone. Program synthesis is a very diverse topic, and it's a little bit difficult to pose it for a large audience of many different backgrounds, so I chose a more application-focused presentation style here. Also, Ruben, my co-presenter, and me, we are going to have a poster tomorrow if you want to have more in-depth discussions about subtopics and so on. So, as said, I'm a PhD student as well as Ruben. We are at TU Delft, somewhere in the Netherlands, and I will presenting this. So the motivation goes as follows. Assume that you're somewhere back in university, and I don't know, maybe it's a bit of a trauma for some of you, but assume that your professor gives you a coding assignment. Gives you a homework, I don't know, you're giving these input strings on the left-hand side, nancy.freehaver at fourthcoffee.com, and you're supposed to produce the output on the right-hand side. You can see these as tests of some sort, and you're supposed to provide a program that leads from the inputs to the outputs. And well, we live in 2026, so naturally we just plug it into our LLM and give the following prompt, give me a program, obviously in Julia, that passes the following tests. And naturally, well, what we do with these prompts is we give two of the main ingredients for program synthesis that are literally a description of what we want, that is a program that passes these tests, and a language in which we want to have these. Well, we wouldn't be here if LLMs would be able to solve all of these, because these are, well, the problems that we are looking at are not your natural or your usual coding problems, but are bound to a specific grammar. So if I repose this problem, well, in this format, you probably have seen this before. This is just copy-pasted from, I think, the default Excel slides from Microsoft, basically. I don't know if you remember these. And then you have this fun little dot at the bottom right side, and you drag it down, and it does some magic things, and this is basically just doing program synthesis under the hood, finding a description and explanation of the input-output examples in form of code. And what it uses under the hood is, well, the second ingredient, that is a grammar. How you read this is quite natural, so you have a type on the left-hand side, a string, and then it basically just completes to something on the right-hand side. So X is our input symbol, and a string can be, well, our input symbol, or it can be concatenation of two other strings, or it can be a string at a certain position, which is then bound by type and so on. And what we are trying to do is we're trying to find the program over this grammar that satisfies the specification. Doesn't get more complicated than this. And then, well, during search, our problem is as follows. Well, we have a partial program. Here it's represented as an AST. If you're a little bit deeper into Julia, that should sound familiar to you. It's basically just a representation of the syntactic form of a program. And this is partial because on the right-hand side, we haven't yet decided on what we want to fill in there, so we cannot actually run the program. And then, yeah, we can just choose any of our rules from the grammar we've seen previously. So we have the whole over there. We can just put in the input symbol. We can put in a space and whatnot. And then the entire question of this talk and the entire question of program synthesis is naturally, well, which of the many choices should we put into this whole to get closer to find a program that actually satisfies our specification? I want to draw the broader picture here, stating that program synthesis, as I said it previously, just needing a specification and a grammar is a very universal framework. So naturally, there's many, many problems that we can formulate in program synthesis that are not just about programs. For example, there is symbolic regression. This is basically, you have a bunch of XY coordinates, and you want to find a graph that fits through them as well as possible, so where X is the input and Y is the output, for example. Then there's this wonderful arc reasoning challenge that some of the LLM enthusiasts of you might have seen before. So currently, I think there's a couple of million on prize money to be won if you actually solve those. It's very small, but basically it's also input-output symbols, input-output examples. You have the figures on the left-hand side, and they are supposed to complete to these squares here on the right-hand side. And basically, you need to find a description that leads from any of the left-hand sides to any of the right-hand sides. But then we can also express other kinds of problems. So a colleague of mine, Issa, she's working on on train planning problems, basically. So this is from a train shunting problem, a very dedicated, very special problem, but I just wanted to put some of the problems here. So basically, you have a train coming in from the right-hand side. It has to be parked overnight, and on the next moment, it has to leave in with a different order of wagons, for example. And again, it's a specification. We know what's going in, we know it's going out, and then our grammar is, I don't know, we have to move this specific wagon on this specific track. We have to couple these specific wagons and so on. And another problem from a master thesis that we're currently having is based on drone design. So again, the specification here is a simulation of a specific track, and then the idea is basically given a specific track and the simulation find the drone design that minimizes the time that it takes to complete the actual track. And then the grammar here becomes a grammar over how you design drones. So you have a base, and the base has 4 different ends, so naturally it's a quadrocopter, and so on, and then you have motors and extensions and so on. And then you have tried to synthesize over this. So What I'm trying to say is maybe you find some of your applications, some of your ideas in here, and if you do, please come to me, talk to me afterwards. Well, yeah, you can, okay. Now, actually back to the topic, and why I'm just presenting this package over here. Why would you actually care about HerpJL? Well, in the beginning of my PhD, when we were very annoyed by the field of program synthesis, we started noticing that the field is just very scattered. Everybody's just cooking their own soup. None of the tools are actually reusable. Like, for example, if you want to evaluate any of these tools on any benchmark, everybody just defines their own benchmark and claims that they're doing the same thing. I don't know, they're using vastly different languages, and it's just very annoying to do anything about it. So we basically just said we're just going to re-implement everything from scratch, such that we can actually build upon existing work. We find this one idea from this one paper and this other idea from this other paper, we just put it together and we have a new search method, a new synthesizer that can tackle these problems. So HerpJL is a Julia framework that provides a unified vocabulary for the program synthesis, such that we can formulate all of these grammars and all of these specifications, and provides a couple of building blocks such that you can easily build your own synthesizer for a specific domain and a specific problem. And we also have some state-of-the-art solvers implemented and benchmarks. And if you want to use it, it's naturally available as the entire ecosystem is available from Julia Hub. So, if we want to formulate the motivating example here, then it goes as follows. Well, we can just formulate it in natural text, as you can see here. We have a macro that defines our grammar, and then basically it's a natural conversion from what you've seen earlier on to this format over here. And the sheer fact that there is a human-readable format of the grammar is an achievement in itself, because previous formulations were just not readable and or extendable. So one of the major issues previously was that basically other methods were building a very specialized tool with a very specialized grammars. So for example, from the Microsoft perspective, but if you wanted to add any rule additionally to the grammar, you could just throw away the entire method because it didn't work anymore, and so on. So what we are trying to do is we want to make these grammars as easy to formulate for anyone who wants to use them and as extensible as possible. And then the second point here, what you can see here is our formulation of a problem, where it's literally just the input-output examples that I've seen earlier on. This is not complicated, right? But it's just our way of formulating what these input-output examples are supposed to look like, and that, again, that these are human-readable is an achievement in itself. Okay, and this then extends to the symbolic regression task that I've mentioned earlier on, the ARC stuff, and many other applications that we've seen before. What Herp does is it modularizes all of the different components into different sub-packages. So we have Herp grammar, which defines all of the actions over grammars, add a rule, remove a rule, whatever, over specifications, interpretations, like different compilers, different interpreters that you want to use. We mainly use the Julia interpreter for many things, but also two other packages, which are Herp search and Herp constraints, which I will get to in just a second. And then there's Herp learn, which is a bit of future work if you want to learn stuff with neural networks. Okay. This was a talk in 2024 already, where it was a short talk, I think, and many things have changed over this, over the time. So the talk, the official name of the talk is What's New in HerpJL, and so I have to put a slide, What's New in HerpJL, since then. There are many advancements on the method side, which I will get to in just a second, but the main improvements are on the performance side and the things that we support. So for example, we now support SMT backends, if you're familiar with solvers. So basically it gives you a way of describing formal specifications. So for all inputs, this, and for all outputs, this and this should be satisfied. We added many more benchmarks that are core to the field, but maybe not to you. We added a bunch of synthesizers that are ready to use for your applications. And I think our main improvement is that we are just way faster on the evaluation side. So previously for I think, a million, like to iterate and evaluate a million programs. I think it took 20 to 30 minutes 2 years ago, and now we're down to like 30 to 60 seconds, depending on the domain that you actually want to evaluate, which is very cool. And it took us way too long to actually get there, but now it actually works, and it's really cool. Okay, I think I spent a lot of time motivating why we're actually looking at this and how you can formulate it, and now we actually want to solve it. Like, we have specifications, we have grammars, how do you actually solve it? And well, the main problem is this is hard, right? If it would be easy, then people would not be looking into, this wouldn't be a problem. And the main thing is naturally that the program space, if you look at it naively, is just insanely large. So for example, the program space grows exponentially with respect to the size of the programs. And then if you want to enumerate these in a brute force manner, then naturally it becomes very slow, very stupid, and it doesn't solve any of these problems. So there are a couple of ways in which you can approach these. And I think in the description that I put alongside the talk, I put this as neurosymbolic program synthesis. This is not coincidental because it's also the title of my thesis that I'm hopefully going to submit in 2 months. So how I post this here is basically we have a bunch of symbolic ways to reason about programs and a bunch of neural ways to reason about programs. And that can help to make the space of programs a little bit smaller to find solutions for the various domains, and it's independent of the domain. For example, we figured out, all of these are backed up by papers that we wrote in the last 2 years, so if you have questions, I can give you citations or forward you to it. So the first problem that we found is, well, the majority of the program space, or the space of the programs that are expressible in our grammar are just useless. So for example, if you have concat x with an empty string, you're just concatenating the input with an empty string, it doesn't do anything. And there's many, many programs like these. So basically what we did is we invented a constraint language that allows us to formulate these constraints in any domain. It's invariant of the domain because it just operates over the syntax. And we have an accompanying constraint solver, which is called BART, after my master student that implemented this partially. And this then works, because it works over the syntax, it's also domain agnostic, and we can use it for many, many different domains. The second thing that we are currently implementing is learning from mistakes. So basically, if you have the example up here, and you figure out, well, this is our the Y is our desired output, it's Nancy space Freehaver, and our current solution just provides a solution which doesn't have a space. We figure out with an SMT solver what was the reason that this actually failed, and then we can push back the signal into our solver, formulate it as a constraint, as you've seen on the previous slide, and then we can figure out that a space must be somewhere expressed in the syntax tree, hence we can reason over programs. This is vastly oversimplified. I'm just trying to get the gist of it without losing you in details. On the neuro side, we are also doing a bunch of different things. I just want to highlight 2 different works that we've done recently. One of them is called Narcissus. So basically the idea is you have an LLM, and LLMs are very good at coding, but specifically they suck when it comes to very specific grammars. So for example, if you specifically ask any LLM to give you a program over the very specific grammar that I mentioned in the beginning, then it's going to hallucinate or just come up, like use its own rules, which is particularly bad for if you have a new or highly specialized grammar that you definitely want to use. So what are you going to do about it? Well, one of the core insights is that if an LLM does something, it's not just useless, but there's many different things within the proposal that we can actually leverage on. So this is part of our recent paper, where we basically just asked the LLM multiple times for a solution, and then naturally none of these solutions actually work, but we are trying to recover some information from structural, from the higher order structure to subprograms that are actually useful and so on, to push them back into our search engine and to try to find programs much more efficient. And this worked out really great. And this is called Narcissus. And then we also figured out that many people just, also in the subfield of neurally guided synthesis, where you actually try to learn a guidance by yourself. So for example, if I'm given this input and this output, I would like to prefer these rules. If I'm given this input and this input, I would like to prefer these rules. This is called neurally guided synthesis. And again, just like in the general program synthesis field, also in neurally guided synthesis, people are just doing whatever, and it's just not comparable and whatnot. So again, we're doing something similar, which is we're providing building blocks for properly comparing and properly evaluating your, I don't know, your fine-tuned models on a very specific domain. And this is soon to be published and submitted under the name of HerbLearn. And we have this standardized way of framing these guidances with this C's and Says framework. So, to summarize, Herb has many different things, and it's a tool to describe a lot of problems. And what we implement so far is we have the neural guidance on the one side, and we have the symbolic guidance on the other side. And for most of the domains, either one of them or even both of them are going to help you to actually find a solution for your problem. And this is what we do. Well, we have neural guidance for deciding what looks promising, what programs should we actually look into, and we have the symbolic reasoning, which actually tells us these are the problems you should definitely not look into because they're redundant or useless or whatnot. And this is what we combine in this field. Full disclosure and final remarks, naturally this will not be a substitute for your favorite LLM. This will not solve all of your coding problems, but will maybe get us a little bit closer to like provable coding or whatever you want to call it. Yeah, we are just a few PhD students who are holding together this project at the moment, so we're definitely not at an industry level, but we're getting faster and faster, and we have more PhD students to actually take over this project. What this library actually can do is we can do small DSLs, small problems, like the problems that I've solved, that I've showed earlier on are very tractable for our library and for our solvers. It will not be able to implement an entire new library, for example. Yeah, and it helps us to define new synthesizers in an afternoon if you really want to. So, if you want to grow herbs yourself, or come talk to me, then you can code yourself with our herb library. If you have equations or models that you want to be expressed, that you want to see expressed in herb, also come talk to me. Or if you want to contribute, or if you have anything that looks like a search, please add herb. And also, please don't forget to water the herbs. That would be important. There's also a QR code over here. And naturally, this also wouldn't be possible without my lovely colleagues. Ruben is a second main maintainer, and a bunch of other people that you can see here. Thank you very much for your attention. And
Okay, we have plenty of time for questions.
Sure.
Hi, I like your work very much. I was wondering, like, have you tried to generate some Julia code from your, have you tried to generate Julia code? You can write a subset of the Julia grammar in using herb,
sure,
and then try to generate it. Like, why I'm asking this is to generate unit tests, something many people are working on that. Mm-hmm. So I'm wondering whether herb could be useful for that.
So first off, the idea of generating Julia code with a Julia library is not new, naturally. I think it was one of the first things that we thought about like 2 years ago. I think we are far from that. I think there's a lot of research on, well, first of automated testing, naturally, but also like specification discovery. Like, for example, if you have a certain test and how to derive from a description of from a formal description of what the code does, what it doesn't do, and then you can derive specifications in form of tests, for example, from that. I think at the moment, Herb is not able to do that, or is not that close to it. But I think with a little bit of engineering over the formal properties of code, I think it should be somewhat straightforward to do that. I can forward a bunch of papers to you if you're eager into looking into that. Thank you.
Any more questions?
Yeah, another question. Like, when you evaluate a candidate program, like, do you protect yourself against some crashes or some excessive memory consumption?
Yes, we do. But the programs that we evaluate on are very small. So naturally, yes, we do, basically. I think the domains that we tackle on are very different, so I'm trying not to give any too general answers. So I'm trying to, I'm walking on eggshells here because I don't want to generalize any statements. I think for string domains, for example, I think it's very easy to learn from mistakes and also track these. But for example, if you move to ARC domains, or like, for example, Ruben is specifically working on biological domains, it gets a lot more complicated in very little time and so on. So yeah, please talk to me tomorrow, please. Thank you. Any more questions?
Any further questions? Okay, I actually have a question. How does the symbolic capability of this compare to symbolic regression.jl? Because that's the, well, I dare say, state of the art in symbolic regression right now.
Sure. I'm not trying to sound elegant, but for example, symbolic regression is a very simplified form of program synthesis where you can do many, many optimizations that you just cannot do in the general program synthesis field. I think we haven't compared, but naturally we will be much worse on the symbolic regression alone. But then any of these symbolic regression synthesizers, if you want to call them like that, will not be able to evaluate on anything else. Yeah. Thank you. Any more questions?
Okay, I think we'll have a small break before the next talk. If the next speaker can come down and set their computer up.
Okay, so hello everyone. Today I want to talk about our little package called Optuna.jl, which allows you to do hyperparameter optimization with Optuna in Julia. To start with, I want to take a quick look at the current state of hyperparameter optimization in Julia. So with the baseline problem of we do not want to tune our hyperparameters or in general parameters by hand. So this could be anything from like your neural network parameters, your learning rates of your optimizers, the tolerances of your solvers, etc. And if we take a look at the current packages inside Julia, they're either just in maintenance mode, so not accepting new features and only maintaining bugs, for example, or are just not actively maintained at all. Or another point that is very important for our package, they do not fully support multi-threaded as well as multi-process execution to parallelize your optimization. So the questions, or the underlying question that we had was, how can we take advantage of already established and mature hyperparameter optimization frameworks that have minimal maintenance overhead for us, since we're just hooking into them, and also have the ability that we can put something on top in Julia if we want to extend functionality, which we'll talk about later a bit more. So what is Optuna.jl? So Optuna.jl is essentially, as I just mentioned, Julia API for the hyperparameter optimization framework Optuna in Python, provided by Preferred Network Inc. And we're using conda package and Python call to load and interact with the Optuna package inside Julia. This means we have full support for all the available functionality inside Optuna, so all the samplers, pruners, and all the database backends, which I will talk about later a bit more. And for your general workflow of using Optuna.jl is you basically have your normal Julia application from where you would call Optuna.jl, and that is basically all that you can see. At the top and underlying Optuna.jl will call Python Optuna, install the necessary packages, and will call your objective function, then you give them, returns the result, and basically runs your optimization loop for you. So how does the Optuna workflow inside look? So the overarching object you have is the study. So this is just your complete optimization run. So at the start, if you want to do a run, this is what you're creating, and this includes all the history of all your optimization runs, your sampler, your pruner, some metadata, etc. So this is just your basic building block on top. And based on the study, there will be trials created. So the trial is then one of those execution runs. So the sampler will take one parameter set from the defined intervals that you gave them, and will then execute the objective function once, will return a result, and the loop continues. And like I just mentioned, internally, it will call the objective function. This is just your function that, based on the parameters that your sampler suggested, will return your objective function score. So like, for example, the final loss of your neural network training, on which you can tell, okay, was this a better configuration of parameters or not? So just for a quick coding example of how that would look in Optuna, this is taken from our examples on our GitHub repo, which you can take a look if you want more details on that. So like I mentioned at the start, you just create your study. This also includes like the storage backend that you want to use, where the information is saved, the sampler and the pruner, and things like if you want to load an existing study or not. Then you define your objective function, which I mentioned. So inside of there, you can see that you can define your intervals in which your parameters are taken. In this case, I just, for ease of use, I hard-coded these into them, into the function, but you can just define it at the top. And then you have your function loop. So this is, like I already mentioned, for example, your your learning of your neural network training that you would do with these parameter sets. And you calculate the objectives, so basically your loss, for example. You turn the results, and internally there's also the point where you would check for pruning. This is important if you use some more advanced pruners that basically tell the system, okay, this does not seem like a parameter configuration that we should keep evaluating, we just stop preemptively. And at the end, you put that in your optimized function. The Optuna.jl will run your optimization loop, and you can get from the study the best trial, your best parameter configuration, or the best values or the best return of the objective function that the optimization loop returned. So what are the package capabilities that Optuna.jl provides for you? So like I already mentioned, these samplers and pruners, there we have full support of all the samplers and pruners that are available in Optuna. These are just some of the examples, and they're inside the packages, but they're fully supported inside Optuna.jl. And we also, in our newly release, are capable of multi-objective searches. So not only one, but multiple objectives inside your function that you want to calculate your loss on. One of the key points that I mentioned in the beginning, the multi-threaded and multi-process execution, is also given due to that we can split the processes and have the synchronized backend, so the storage where all your metadata and sample and pruner, etc. are stored. This is your synchronization point where all your threads and processes get their information so they can be operated independently. So that also means that your high-performance code, or the code that needs to perform well, like your tuning of your neural network, for example, inside your objective function, is never called outside of Julia. So this stays inside of Julia. You also can get an overview of your experiments based on the backend that I mentioned. So these are mainly just databases that run in the background. And they, like I already mentioned, are things like the artifacts that you store during your runs, your metadata, or just the trials in general. And for that, you can take advantage of a small little package that we called Optuna Dashboard.jl, which I'll show you real quick. It's just the visualization of the dashboard that is already provided by Optuna. So this is just what it looks like. It might be a bit small, but this is just as an example. For on the left, you can see all the trials that were run in your optimization run, some of the trials that were pruned, so preemptively stopped, and just general information about the trial that you selected on the left. There's also many more information, like here you can see, for example, the importance of your hyperparameters, so which parameter had the most influence on your result of your objective function, just the general history of your objective runs, or in the bottom left, like your best trial that the optimization run returned. And you can take a look at that. There's many more information like correlation of parameters, etc. So it's very expansive. So what then are the advantages and trade-offs if you use Optuna.jl in comparison to like one of the optimization frameworks that exist? So the big advantage is we can take the advantage of the full Optuna ecosystem. This means we support all already implemented features, and more features that are added to Optuna are very quick to adopt because we only have to write the corresponding function calls or API calls to Optuna. And we also offer a full workflow in Julia. So what that means is you do not have to switch language in your workflow to use Optuna. You can just use our predefined functions and structs and do not have to leave Julia to use the capabilities of Optuna itself. This also means we can drastically reduce our maintenance effort in maintaining this package, since we only have to keep the API calls up to date and do not have to worry about, oh, this functionality is not working because that's not on our end, but on the Optuna end. We can, the guys at Inc. can take a look at that and fix the issues. Like I already mentioned in the beginning, one of the more important points for us was also that we can extend the functionality. So we implemented our code base that we can, for example, add new solvers or pruners that are written in pure Julia, and instead of routing the call to Optuna, they are then called in pure Julia and returned there, so nothing even gets out of the Julia runtime. There are also one or two trade-offs. For example, in this case, we have a Python environment that is running in the backend, since we have to call Optuna, but the user doesn't ever see this, so this is all handled by the package itself, and the user does not have to worry about dependencies or versions of those dependencies. That is all handled by Optuna.jl. And since we are crossing language boundaries, there is a performance trade-off, since we are calling the languages from each other, but in our eyes, it's the non-performance critical code, since it's always just getting new parameters, reporting results. The performance critical code, like the optimization of your neural network or the training of a neural network, for example, is still inside of Julia and is only executed in Julia. And with that, I thank you for your attention. You can take a look at the GitHub repository with this QR code, and I'm free if you have any questions regarding the package.
Okay, we are taking questions. Any questions? And if the next speaker can go set their computer up as well, if they're here.
Hi, thanks for a nice wrapper. I was wondering, you mentioned the Julia ecosystem, maybe a lack of capability was the multi-threaded support, similarly to the comment you made regarding the low cost of transfer, that it's not the critical path, performance path. Do you see in practice benefits from this Optuna multi-threaded, considering that in typical scenarios the single model will occupy full resources? So what kind of context do you see, like the benefits of Optuna compared to, let's say, sequential approaches that I think may exist in the MLJ ecosystem?
Yeah, so it's a good question. The main advantage in compared to, like, you mentioned sequential approaches, is that in this case you can think of it as, if you have a problem that that is very favorable for high parallelization and also multiple machines, you do not have to worry about anything. But that's also only the case if you are, in this case, the objective function requires you to have a massive parallelization, because they are quite expensive to run, like, for example, training of very large neural networks where you want to parallelize your optimization.
Any further questions? No? Okay, we'll just have a small break before our next speaker. Okay.
I'm a software engineer at JuliaHub for in the consulting services team. And today I'll be talking about my package, this package that I wrote called basemodelica.jl. So first of all, I should probably make a disclaimer that I'm not really a Modelica person. So this package actually came about because it was probably a discussion at JuliaCon, JuliaCon probably about 3 years ago, about, someone had this idea of a flattened Modelica model, and being new to the company about 3 years ago, I needed something to do, so I kind of got this side quest. But okay, so what is base Modelica? It's basically kind of an intermediate representation for Modelica models. So it's a format proposal that proposes kind of standardizing and simplifying Modelica models, kind of a standard for a flattened form of Modelica that kind of simplifies the representation of Modelica models into basically, hopefully, just equations and variables and parameters, plus maybe a few other things like events, clocks, things like that. But yeah, so the idea behind it, the core purpose of it is to really kind of enable model exchange and to simplify compilation pipelines. And also, get rid of things like tool-specific translation issues. So, for example, a lot of the kind of industry standard Modelica compilers, they might have their own special semantics for a lot of things. This is kind of meant to be a way to bypass those and have kind of a standardized implementation that all Modelica tools will be able to use. Another thing is that it kind of is meant to separate the front-end concerns from back-end concerns. So for example, if you want to write some Modelica model in, the open Modelica kind of dialect of Modelica, but you want to use something like Daimola's, compilation pipeline instead. This is kind of meant as a way to enable something like that, where you can have kind of a separation of concerns between things like the GUI and then as well, and then things like the actual simulation semantics. So like I said, so lowering the barrier of entry is kind of a big purpose for base Modelica. So writing a complete compiler for the full Modelica specification is a pretty complex task, right? So there's a lot of high-level structures in Modelica, and it's pretty difficult. But the base Modelica, so one of the ideas behind base Modelica is to just have a stripped back specification that enables easier compilation, things like that. So right now, the only tool that can output this base Modelica stuff is Open Modelica. So this is an example of a flattened base Modelica model. Like on the left, we've got a Newton cooling model, and really this is very much just like a standard Modelica model with a couple of differences. Like it's got a base Modelica identifier right at the top. You need a couple of different, you need the tick marks around the variables, things like that. But the major differences are, so with base Modelica, there's no object orientation. The variables are all flat scalars. There's no procedural algorithms. You have to have explicit, so equations are limited to basic mathematical operators and explicit first order derivatives, and you do not have connect equations. And all of these are kind of in flux as well, because the actual base Medelica proposal isn't set in stone yet, and they're still trying to figure out exactly what pieces of Medelica will end up in base Medelica. So base Medelica.jl is basically a way to translate these flattened base Medelica models directly into Modeling Toolkit ODE systems, right? So it is what it says it is, so I can take something like this Newton cooling method and plug it into Modeling Toolkit and then simulate it with ordinary DivQ, or use any of the other SciML ecosystem packages, right? So far, not all of the features of base Medelica are supported. A lot of them are. A lot of the basic ones are, but it's a little bit difficult to target a kind of moving specification like this. So I've got data types, equations, initialization equations, when equations, discrete variables, stuff like that, and parts of the standard library, like the mathematical library, are implemented. But I don't have things like records, custom types, custom functions, or arrays, matrices, and indexing, which that's kind of a new thing that array variables are something that they just recently added to the base Medelica standard. So let's see. So one of my collaborators implemented a testing pipeline for base Medelica. So it basically takes all of the Medelica a huge chunk of the Medelica standard libraries and examples, flattens them into base Medelica, and then just tries to simulate them using base Medelica.jl, and then validates it against the reference implementations in the Medelica standard library. So things like, electronic filters, the CHUOS circuit works, ideal diodes, that's really a very small subset of what's being tested. There's things like lightning strikes, mechanical stuff, hydraulics, all that kind of stuff is in the Medelica standard library, and it all tries to get simulated using base Medelica.jl. So not all of it is working, of course. So the Open Medelica export, it exports, so out of 457, it's 454, right? And then, so I'm able to parse all of these using the parser. But then the base Medelica to Modeling Toolkit translation, we lose a significant amount of models. A lot of that is because so there are a few issues with exporting Open Medelica where it's technically, it fits the grammar for the language, but it doesn't actually, it violates some of the rules of Open Medelica, some of the rules of base Medelica. Another issue is, mismatch between different capabilities of Modeling Toolkit and what can be represented in Medelica itself. And then we lose a few more when we try to generate the ODE problem. A lot of that is initialization issues. And then the actual simulation, we're able to get 70 simulations running, and then 55 of those actually match the reference implementation. So there's still quite a bit of work to do. I just wanted to show, so this is a CHUOS circuit. It's, a chaotic circuit. So here's the Medelica model on the right. So we can see it's just got parameters, variables, and connect equations. The base Medelica model looks like this. So this is all flattened. So you can see that we've got all scalar variables. We kind of take all of the nodes as a variable. We have parameters, and that's not even it. We have even more. And here's the equations and some assertions and even more equations. So we can see that this thing on the right gets flattened down into a pretty large base Medelica model. And in order to simulate it, all you have to do is, the Modelica has these kind of annotation, like experiment annotations. I'm able to parse those and read the stop times and the intervals, just create an ODE problem straight from it, straight from the file, and then solve, and you get the classic double scroll attractor. So this is exactly what it should look like. So just talking about some challenges. So the base Modelica specification is defined as Modelica minus a bunch of language constructs. So there's not really a set like grammar file. I had to go through and subtract things from the Modelica grammar files. And not being familiar with Modelica, that was kind of difficult. There are feature mismatches between Modeling Toolkit and Modelica. We're moving towards feature parity. We're getting a lot more capabilities, but there's still a few things that don't work. And then there was also kind of an issue, okay, is this Open Modelica messing up? Is this like an AST evaluation bug, or is this some numerical issue? It was kind of hard to parse between. And I'd like to thank, Francesco Casella, Andreas Humerman, and Julia Hub for employing me. And I've got some useful links. Anyone have any questions? I think up there.
So as far as I understand it, the base Modelica is still not like a causalized model or anything close to a ODE or a DAE, and there's still a lot of work the compiler has to do, in this case MTK, and there's lots of choices that were different when designing MTK against Modelica. So I was wondering, do you think it's ever feasible to get like the full Modelica standard library running in MTK this way, or is base Modelica the wrong interface for that?
I think it's feasible. So it just will take kind of. So I think it's a case where the first 90% of models will be relatively easy, and then the last 10% will be pretty tough, just because of the feature gap between Modelica and MTK at this point. But like I said, we're quickly reaching like feature parity, and a lot of things like events, synchronous clocks, things like that are coming to Modeling Toolkit. So I think it's definitely feasible. As for whether base Modelica is the right way to do it, I'm not sure about that. But I do think it's definitely feasible if to take those base Modelica models someday and to actually be able to simulate all of the standard library. It's just a matter of putting in the work and making sure that the translations all make sense. Yeah.
Okay, we have another question over here.
More like a comment on this question. I think you should have a look on the library om.jl, which is, I guess, doing exactly what you wanted to ask. So it translates normal Modelica to MTK. And I think it's by now quite good at compiling most of the standard library.
Yeah, so that answers the question, really, yeah.
Okay, do we have any further questions? No? Okay, can the next speaker set the computer up?
The first question we should probably answer is, what even is a point cloud? And it's fairly simple. Just think of it as a representation of some kind of physical object, like this cute fox here, for example. And we do this representation basically by a list of points. And those points typically live in 2 or 3 dimensions, but for the sake of this package, that doesn't matter, it can handle arbitrary dimensions. And then besides those point coordinates, we also have a weight for every point. And the weight is always depicted in my illustrations by the size of the point. So that's like not a physical size, but the weight. And the idea behind this weight is that by default, the weight would be 1 for every point. And then if it's some integer, it's like this point existing that many times in the point cloud. But again, it can be some arbitrary non-negative number, just indicating the relevance of this point in the point cloud. And then that's it. So we have the coordinates and the weights, but we have no like surface information or any other kind of feature you might know from other point cloud applications. And now, hypothetically, if you were to go ahead and build a Julia package that does, say, a point cloud registration, you would want to have a struct like this, where you have a vector of vectors for the points, and then another vector for the weights. This is, of course, heavily simplified. Don't do this at home. Of course, in principle, it works a bit differently, but the general idea is that. So that is a point cloud, and now, what is point cloud registration and why should I care for? And for that, I invite you to take a look at these 2 point clouds. And I hope you agree with me that when you go from one point cloud to the other, all that really changes is like the angle of the tail, right? The red point cloud has the tail a bit lower, and then the blue fox, let's say, has the tail a bit higher. But if you ask the same question from the perspective of an individual point, and let's say we pick the point with index 218, then it stops making sense asking what happens when I go from one point cloud to the other, because, I mean, yes, like technically you can ask what is the difference in coordinates or so, but it doesn't mean anything. I mean, this point is somewhere in the back, this is at the tail, and overall their difference will be largely explained by this point cloud being at a completely different position and orientation. So yeah, we can't really ask this question unless we do point cloud registration. So you can really understand point cloud registration as the process of normalizing point clouds in terms of their frame of reference. So that means that you try to put them on top of each other in plain English. We also call this aligning them or superimposing them. And then also normalizing the point clouds in terms of the number and order of points. So here, these 2 point clouds have a very different number of points, and here, after registration, the number of points is the same, and we can also do actually this comparison in terms of a specific index. We can ask what happens to this specific point, and it does reflect this tail movement that we were after. Okay, so that's what we try to do, and that's what this package can offer. Let's go to this step by step, and the first step we would have to do is called rigid registration. So this is really about this getting the frame of reference, right? Trying to superimpose 2 point clouds. And in more formal terms, the question is the following. So we have 2 point clouds, one we call the source, another one we call the target, and now we try to move this source to the target, but the source is rigid, so it's like cast from solid metal, you can't deform it or anything. All you can do is take the whole thing and move it through space by either rotating it, translating it, or maybe reflecting it. I say maybe reflecting it because like you also can't reflect the physical object, so that's why we typically don't allow this in rigid registration, but sometimes you do want this, and then again, the package offers it, it's just like off by default. In any case, that's what we want to do. Rotate, translate, maybe reflect the source to match the target. And how do we do this in the package? It's quite simple. You load the package, obviously. And then there is this rigid registration function where you just give it the source, the target, and some algorithm, which we'll have to discuss in a second. And this will give you a motion. And the motion is generally just this combination of translation, rotation, maybe reflection. And then you can apply this motion to the source point cloud, and this will give you a registered source, which is then superimposed onto this target, so they match in their position and orientation. So about this algorithm, how would you actually do this? And a very simple first idea that you could have, and that people have had before, is the following. Let's say we have 2 point clouds again, but we also have some other information. We know that both point clouds have the same number of points, and we also know one-to-one correspondences between the points. So for example, we know that this point here in the paw corresponds to this point in the paw, and this point in the ear to this point in the ear, and so on. We all know this for all the points. And then what you try to do, at least conceptually, is imagine attaching some rubber bands between pairs of corresponding points, and then you let those rubber bands snap together, and this would bring the 2 point clouds to lie on top of each other. And as I said, this is a very well-established idea. A guy called Wolfgang Kapsch, for example, wrote down an algorithm to do this, so we can call this the Kapsch algorithm now, and it provides the solution to this problem in a closed form, and you can actually write this down in like 3 lines of Julia code. So it's very, very simple to do, which probably is the reason why this is now, at least to my counting, the 4th time that someone has done this in the Julia ecosystem. So as far as I know, there is the coordinate transformations package from Julia Geometry. Then there's the literal Kapsch package from a group doing structural biology. There's the biostructures package, and now this package for all implementing the very same Kapsch algorithm. So you might be wondering, and I would understand this question, why? Why have it another time? And it turns out that the other implementations leave quite some room for optimization. So when we look at some benchmarks and just go ahead and take a bunch of point clouds, try to register them using this Kapsch algorithm as it's implemented in the different packages, it turns out that the other packages need much more time than this package. And in fact, just the time that the other packages wait for the garbage collector, which is this orange part of the bar, is about the time that this package needs to finish the job. And this is maybe the first key takeaway of this talk. Even if you're not interested in all the other fancy features of this package and all you want to do is just standard Kapsch algorithm, it probably still makes sense to use this package because it's just so much faster. Then why is it so fast? Well, it comes down to 3 of the usual culprits, I would say. First, for the compiler, it just knows a lot of stuff. So, for example, it knows the dimension of our points. We're using the S-vector type from the static arrays package, which has its length as part of the type. So the compiler can understand this, do some loop unrolling and inlining and all this magic. And then for the weights, I said that every point has a weight, but often we don't actually need that, and we just stick to this default of each weight being 1. And in this case, we don't have to store all those weights explicitly, we store them implicitly, and we do this using the fill arrays package. Again, the compiler can understand that, and it can then compile away all the code dealing with weights, actually. For the memory cache, it's quite nice that we only have to pass over the points a single time, so they have to be loaded into the cache only a single time. And the garbage collector has more or less nothing to do because we practically don't do any dynamic memory allocation. So this is now specifically true for the implementation of the Kapsch algorithm, but the principles apply to the other algorithms implemented in this package as well. So there was like a clear focus on the algorithm engineering and performance details. And speaking of other algorithms, you might be wondering now, if this Kapsch thingy is so nice and so fast, why bother with anything else? Why have this full-blown package? And I hope this becomes clear when we look at the result of the Kapsch registration, which doesn't look so nice, does it? And what happens here is that the tails are obviously an outlier to this rigid registration. I mean, there are at different angles, you just can't rigidly register them, but the Kapsch algorithm tries anyways. And then what happens is it makes a compromise with everything else, and then just everything is badly aligned. So yes, this Kapsch algorithm has the undeniable advantage of being very, very fast with its closed form and all, but in practice, it just gives you very subpar results in the presence of outliers. There are other algorithms, such as the one with this beautiful name, Geman-McClure majorization minimization, which does not have this problem. Because here, if you look at the result, you see that you actually don't even see the red point cloud, or at least its body, because it's just perfectly covered by the blue one, just as we wanted, and only the tails are left as they are, because, again, they are outliers in terms of rigid registration. So this method is very robust to outliers, but you pay for that by not having this closed form solution anymore. So in optimization language, it's not a convex optimization problem anymore, and it's now an iterative algorithm. But this actually sounds worse than it is in practice, so it's still plenty fast, works very reliably. There is another problem, though, that both of these algorithms share, which is they need those correspondences. You have to tell them this point in the source corresponds to this point in the target, and this point in the source corresponds to this point in the target, and so on. And there are actually legitimate applications where you have this kind of information. So if you're working with protein structures, for example, you might have a sequence alignment. If you don't work with protein structures, it doesn't matter what a sequence alignment is. In general, but there might be the situation where you don't have this information. And if you've ever worked with rigid registration before, you might have come across the iterative closest point algorithm, because its very purpose is to deal with this lack of correspondences. And it does so by taking every point in the source and comparing it with every point in the target. So we don't need correspondences, but on the flip side, this brings us into quadratic runtime behavior. And that means, in practice, it's rather slow. Okay. There's some room left on the slide. So yes, fortunately, there's yet another algorithm. And this one is based on the kernel correlation. And it actually ticks most of the boxes. It works without correspondences. It's fairly robust to outliers. And it still has a linear runtime. And I find this quite marvelous, actually, because conceptually, it still has to compare every point in the source with every point in the target. But due to some clever pre-computation, we can actually still achieve this linear runtime. We don't have the time now, unfortunately, to go into all the fancy mathematical details of those algorithms. I just want to highlight a few things in this overview. One is, yes, the captions and the iterative closest point algorithms probably are like the industry standard default ways of doing rigid registration, but I would actually advise against using them, because in practice, when you use the Geman-McClure or kernel correlation-based methods, you get much better results. And depending on if you have correspondences or not, you should choose one or the other. And this is actually reflected in the API of this package, because so we had seen this rigid registration function before, and we saw that you can give it a source, a target, and an algorithm. But actually, if you leave away the algorithm, it will choose one for you, and you just tell it if your point clouds are ordered or not. So ordered means that you promise that the first point in the source corresponds to the first point in the target, and second in the source, the second in the target, and so on. And depending on this information, it will then choose one of the two algorithms for you. And I assume that the majority of users of this package probably can stop here, because I think many people are just interested in the rigid registration. And therefore, I think it's quite nice that you have this very brief and convenient API for doing so. However, other people, such as myself, need a bit more. That's why I implemented it. And this a bit more is called non-rigid registration. So now, after we have like superimposed our two foxes here, we really ask ourselves, so what is about this tail? How can we also make this, the tails of the foxes match? And in non-rigid registration, the question we're now asking ourselves is, we again have a source and a target, and we assume that we have previously rigidly registered our source to the target. And now we ask, can we deform the source such that it matches the target even better? And the problem here is that the term deformation is a bit vague. And I try to illustrate what I mean by that in this slide here. And maybe you agree that not all deformations are born equal. I mean, these two here on the left, they look kind of plausible deformations. This one on the right, not so much. It's maybe completely twisted or so. So there's another question we have to ask ourselves, namely, what even is a sensible or plausible deformation? And the answer to that very much depends on the algorithm that we choose for non-rigid registration. So that's what we will look at next, because there is now the non-rigid registration function, which works very similar. You give it source, a target, and an algorithm. And the question is, what choices do we have for the algorithm? Quick disclaimer, this slide and the following 1 or 2 minutes will be a bit dense, and I appreciate that it's going to be a bit of name dropping. Again, we don't have the time to explain this fully in detail. I just want to give you an overview of what's happening here, and there are many more non-rigid registration algorithms out there. Those are just the 4 that I have implemented. All right. The first one is probably, again, kind of the most popular choice. It's called coherent point drift, and there what we do is we say that we transform a specific point by taking this point in the source and adding some displacement vector that depends on the source point to it. And now we require that if 2 source points are similar, we also want that their displacement vectors are similar. And if you think about it, this means that there's some kind of continuity in the displacement field. All right, second option you have is the distance preserving method. And there we say that if 2 source points are neighboring, because they're maybe closer than some threshold or so, then we want that after they've been transformed to match the target, their distance is still similar to the distance they had before. And this effectively means that you have some kind of scaffold in your source and you try to preserve this scaffold. Third option is the earth mover method, and this is based on optimal transport, if you've heard of that before. And here the idea is to try to move as little weight as possible while we transform the source to match the target. And then finally, the fourth option is a very fancy one called divergence-free, where again the idea is that we transform every source point by adding some displacement vector. But now we require that the divergence of this displacement field is always equal to 0, so there's never any mass created or lost. Again, I understand that this was a bit abstract. Sorry if I lost some of you. Now would be a great time to come back, please. Those are some of the algorithms implemented. And what I really want to say with this is that they all have different ideas of what a plausible or sensible deformation is, and you should choose accordingly when you do non-rigid registration. And with that, we can actually put this all together and do the whole point cloud registration pipeline now. So in the beginning, as I said, we have a source and a target, and they have roughly the same shape, and we want to bring them together. So the first thing we do, as I said, is perform rigid registration. And this gives us motion, and then we apply this motion to the source, and this gives us a rigidly registered source. So now these two, the rigidly registered source and the target, lie neatly on top of each other. They're superimposed. And when we now plug this rigidly registered source into the target, and the target into the non-rigidly registered function, registration function, and specify some algorithm, as we've discussed before, this gives us a deformation, and we can apply this deformation now to the rigidly registered source, which gives us a non-rigidly registered source. So now if you compare this one with the target, if everything went well, they now should match pretty much exactly. And then we can do a last step, and for that we don't even need any more code, because what we just do is we compare the rigidly registered source and the non-rigidly registered source and do whatever we wanted to do with our point clouds in the first place, because they now have all the properties we need. They sit neatly on top of each other, they are superimposed. They still have the same shapes as we had in the beginning. We still have tail up, tail down, so to say. And they now have the same number of points, and their order also matches. So we can actually do this point-to-point comparison for a specific index. So yeah, this is what you can do with point cloud registration, and you can do with this package. There are some other things you can also do with this package that just comes in handy in my experience. So I just quickly want to show this. And one thing is that sometimes you don't even work with point clouds in the first place, but rather you have something you could call a density. So think of an image or a volume as voxel data. But actually you can quite trivially transform this into a point cloud by just placing a point at every pixel or voxel location and then using this intensity as the weight of this point. And you can do this using the density to point cloud function in this package, where you just give it some d-dimensional array, and it will give you a d-dimensional point cloud. and it just uses the indices of the pixels or voxels as the coordinates, which often actually is enough, even though those coordinates don't really make sense, but like relative to each other, they work. If you happen to have more like sensible coordinates from your domain, you can actually do this as well. There's the dimensional data package, which provides the dim array type, and there you can attach physical axes to your arrays. And if you do that and stick this into this function, it will actually use like the coordinates that make sense for your scientific domain in the point cloud. Another nice feature is that of thinning. So often it happens that your point cloud has way more points than you actually need. And at the same time, the algorithms take longer if you have more points. So you might want to reduce this number of points, which you can do in 3 different ways in this package. One is to say that please give me a point cloud that represents the same shape, but where the neighboring points have a certain distance to each other. Or you could say, take a grid with a certain size, place it over the point cloud, and give me the centroid in every grid cell. This looks a bit funny, admittedly, but it's very, very fast. And then finally, you can just say, please represent the same point cloud or the same shape with exactly this many points. So that comes quite handy, and actually I do this whenever I do some point cloud registration. First step is always thinning this down because, yeah, you typically have more information than you need. And before I now let you go to lunch, I want you to take 3 messages with you. The first one is that if you're working with point clouds, you probably want to normalize them, and normalizing point clouds means registering them. And then this package is for you. And if you're not working with point clouds, but with density arrays instead, actually, this package still might be for you because there is this density to point cloud function where you can stick this in and then thin down your point clouds, and then you have your nice point cloud to work with. Second message that I really want to spread like a gospel: friends don't let friends use the naive captcha algorithm. I know it's like the standard and it's what everyone does, and it's very fast and convenient. But if you just use the rigid registration function from this package, you still get a fast and convenient method that is also very robust in the presence of outliers. And finally, if you're doing non-rigid registration, you should think about which algorithm you use, because this influences what kind of transformation you assume to be plausible. All right, and with that, I'm at the end. You can now check out this package if you want, and you can check out the code also. It's hosted on Codeberg. Everything is under this QR code, and if you'd like to discuss about more features, integrations with other packages, shoot me an email, contact me via Mastodon, or we can also chat now. So thank you very much.
Okay, we have time for a few questions.
Okay.
Maybe you already mentioned this. What happens if you don't have the same number of points in your source and your target?
That doesn't matter if you don't need correspondences. So then you would use an algorithm that doesn't need correspondences, such as this one. I mean, here it's the case, right? They don't have the same number of points, and then you use less kernel correlation. No problem.
Thank you. And also, I'm not using cloud points yet, but if I would, it would be more like in 5 to 10 dimensions.
Mm-hmm.
Do you see any impact on the calculation time?
Well, I mean, I think it's, let me guess, I think it's linear in the dimension. So yeah, should also work with higher dimensional point clouds. I mean, you have to really ask yourself if it makes sense to have like a rotation and so in this 5 or 10 dimensional space, if the analogy of the Euclidean space makes sense as a model for your application, and you really want to have this like Euclidean distance registration. But if it does, then no worries, you can do it with this package.
I'm not sure of anything yet. It just opened some ideas in my mind. So, thank you.
Great talk, thanks, great package, I'll definitely use it.
I have a question about, for the iterative closest point method, my implementation is sometimes sensitive to initial conditions. Maybe that's a mistake, or is that a property of the algorithm, and did you fix it? And separately, maybe can you talk about uniqueness? Like if you register a cross shape onto another cross shape, you could rotate it all sorts of ways and it matches perfectly. How do you target uniqueness in your packages?
So did I understand you correctly? You said your implementation is sensitive to the, yeah. I mean, exactly, that's a problem. And in fact, I mean, those are just two sides of the same matter, right? This uniqueness and initial conditions. You just have many local, non-optimal, non-global optima in this like optimization landscape. So there are three methods I use for this. One is just multiple restarts, so just choose a random initial pose and try to go from there. The second one is some simulated annealing. So in these two cases, you have like some kind of scale parameter, which makes this optimization landscape more rigid or more smooth. So you start with the smoother one and then make it finer and finer. And finally, I mean, from machine learning, we know the stochastic gradient descent, where you always just use like a part of your data in each batch for each iteration. And since those are iterative algorithms as well, you can do a similar thing. So in each iteration where you improve your registration, you only use parts of the points, and this also gets you over the local optima. So this very much helps with like the dealing with sensitivity to the initial position. And then the other question about the when there are multiple legitimate solutions, so to say. This is also dealt with by the multiple restarts thing. So you will just find them if you do enough restarts, because different restarts will land you in different of those solutions. And then there's a potential like keyword argument you can give to the functions, where you say, please let me do whatever I want to do with all the results I find for every restart. And then you can just collect them, and then you have all your different poses for the different possible solutions. Yeah.
I think we have time for one more question.
Can this be used for non-physical associations, like maybe optimization routines and like portfolio management? Like, let's say you have resource distributions and you want to do an alignment for optimal allocation. Would you use this library for that?
So the question was if you can use this for other situations where like, so we were talking about like, I think optimization and operational research. So where the point clouds don't represent physical objects, right? And I think this ties down to the first question we had. And it really depends on if like the Euclidean space with distances and angles makes sense in this case. If it does, then yes, probably. But I guess in many situations we use point clouds a bit more abstractly than that, and it's not like in some physical space where. So if angles, for example, don't make sense in your situation, probably it's not sensible to use this package. It doesn't use angles, but like that's kind of a good test. If you say no, there's no proper angle, then probably there's no sense in doing rigid or non-rigid registration with this package.
Okay, fantastic. That's lunch, guys.
Thank you very much.
There's a lunch with ASML at their booth at 1:45. Just to make you aware of that. Otherwise, regular lunch.
Thank you.
So, oh, it's loud. Hello, everyone. Welcome to this afternoon session of the general. We started about half an hour later because unfortunately we need to put out one talk. But nevertheless, we start the session with a talk from Jacob Quinn about Rousseau.jl. And he want to talk a bit more about platform native async IO primitives for Julia. Take it away, Jacob.
Can you hear me? There we go. Okay. Yeah, I'm Jacob Quinn. We're going to talk about réseau today. It's a French word meaning like network, mesh kind of thing. So it makes sense for a network-based package. Quick introduction. I work for a business called Christofferson Business Travel. We do corporate travel, and we're building a tech platform from scratch for that. So you can do all your booking and everything, and we use Julia as part of our stack on the back end, which is fun. But also we need good, solid, kind of production-grade packages to help kind of power the actual back-end services that we're using. So today I'm going to talk about réseau. First, a little bit of motivation, context for why this package exists. I've been the primary maintainer of HTTP for a long time, started the package and kind of built up things over time. We went through like a couple different kind of rewrites of sort. But there was always this lingering problem of lower level issues that were just really annoying to deal with. And sometimes we could come up with a good solution. One of those was like replacing embed TLS with OpenSSL, and that helped in some ways, but also kind of complicated things in other ways. The fact of the matter was it was just really hard to deal with a low-level libuv kind of socket implementation connecting with an OpenSSL C library that kind of had its own, quirks and constraints and requirements, and then trying to, shepherd that all together, as a Julia wrapper, at the HTTP layer, and make it all work and cohesive and synchronized and nice. So this is kind of talking about some of the issues that we saw, but there was a number of packages, or there's a number of issues that kind of cropped up over time, dealing with like the sockets, libuv side of things, the timeout semantics, and for a long time we were trying to just do timeout stuff like at a very high level, but it actually didn't go down and integrate into the C library layers. There was all these TLS issues that came up, and some of those were just the integration with the TLS libraries. Some of those were just, the TLS library themselves. And then that kind of snowballed into other layers, like affecting our WebSocket implementation, the fact that we didn't have HTTP2, and that felt like such a huge thing on top of what already felt like kind of a shaky foundation, and then just general performance and control. On the performance side, there was a hard ceiling that we were dealing with. And part of that is just the nature of, having a global IO lock, having a single-threaded, libuv event loop. And this is a bit of a extreme case, but trying to maximize the bandwidth on a very huge, cloud machine that has 30 gigabits per second in terms of egress bandwidth, outbound bandwidth, so like the put side. We just were running into these limitations that were kind of out of our control, and that didn't really affect a lot of the day-to-day kind of performance. But when you're running in a cloud on a cloud machine, doing high performance throughput into a cloud storage, that really does become a limitation where we can't fully saturate kind of the network bandwidth that these really big machines can offer. So that's a little bit of the background and motivation for all of this. Basically, it was just, it was getting very annoying to try to deal with all of these issues. And every time a new TLS bug was opened, it was like, okay, let me like put my goggles back on and my hazmat suit and try to like dive into like, what's going on here. And that's not very fun. So one of the pieces I was looking at for a long time was, what are the other kind of industry standard, solutions, network stacks out there? Go obviously kind of has their full Go, pure Go kind of network stack. Rust TLS has over time kind of grown their own pretty solid vertically integrated stack. This one was attractive to me. So AWS has open sourced it's called their CRT, Common Runtime Libraries, where they've kind of built up their own standard lib of sorts for network operations. So cross-platform, all OS, all written in C, all kind of modern, really well documented C. And so this was really attractive. It felt like an easy way to kind of wrap these libraries and then expose them in Julia. So I did kind of an initial prototype where we kind of I actually compiled a bunch of these libraries all together in one like combined C library that basically did exactly what I wanted. It was like very simple get and put requests, wrapped it in Julia, and then ran it on this like really big beefy cloud machine, and it was great. Great throughput. Sorry, did I touch something? It was really great performance. I'll just talk loud if this isn't working. And we didn't run into any ceiling. So I was like, okay, this is awesome. Okay, this is the way forward. But then it was, a lot of work around trying to take all of these C libraries that all had upstream C, repositories in AWS, wrapping them all in, Julia kind of wrapper libraries, trying to automate the, keeping up with those releases. There were missing features. There were bugs that we ran into along the way. Some of the times we could get those bugs fixed. I contributed a few upstream kind of fixes. But there were also cases where there were just missing features. One of them was like a server-side WebSocket upgrade path. And they kind of just flat out said, this isn't a high priority. This isn't something we need. And, we're not like super keen to merge stuff that we're not, can maintain ourselves. And so the PRs just kind of sat open forever. So it felt like maybe we could do that. Maybe I could just, I ended up forking this one library that we needed and had the feature kind of patched on top. And we kind of had this thing where I was like pulling in upstream fixes and then rebasing my patch on top, and we'd use that. But it wasn't ideal. So eventually, AI got really good, and I said, hey, what if we just tried to port all of the AWS code to pure Julia? And then we just kind of had our own Julia copy of that. So I, set Codex and Claude on a mission, said, hey, go, start figuring this out, start porting this. All the code is there, all the C code is there. And AI is pretty good at just kind of copy and porting, translating code. So it took a few weeks of figuring out some of the nuances here, but eventually it did, and it was pretty decent. And the performance was pretty good, but there ended up being some kind of blockers, and as I kind of dug into it and I was trying to figure out, especially around trying to make this trim compilable, okay? That was one of my big goals in all of this rewrite was I want to be able to make a trim compiled binary that is an HTTP server or an HTTP client and can do those things. And the model of the CRT is I'm starting up however many independent threads, and then they are the IO event threads, and they handle all the IO. So if I'm a task, if I need to do IO, I need to essentially talk to the event loop group, okay, and say, here's what I'd like to do, here's my data, and it says, okay, I will go run this for you, and then let you know when it's ready and pass back your data. But it's really this handoff of sorts, and all of the I/O operations happen on these event loops that the AWS threads kind of own. We can kind of do that model in Julia, and it was working for the most part. The problem becomes when you try to do this passing of data between threads and function callbacks, and pretty soon that gets really complicated with trying to be trim compilable, if that's a word, and then managing kind of the back and forth there. So it ended up feeling like I was fighting against the architecture a lot. And so I kind of took a break for a week or two and said, you know what, let's go look at the Go model. Let me dig into kind of how it works, what it's doing at the lowest levels. Once again, I kind of said, okay, I kind of understand the system here. You know, AI, let's start a port. Let's start just porting this straight over to Julia. At the lowest level, we had to kind of massage, you know, what that looks like. But the results were dramatic, in my opinion. It went from like weeks of feeling like I was fighting the architecture and getting things to work and then still running into issues to it was done in a couple days. And it actually looked very clean and very much like idiomatic Julia code, and all the performance. Oh, and it was actually trim compilable almost from the beginning. So that was a very early signal to me of this feels like a much better kind of approach. And you know, at the lowest level, the idea is that you know, Go has Go routines. They have kind of a task-based model that's not tied exactly to threads. But essentially, each task owns their own I/O, okay? So they can optimistically try to do their own I/O on their own sockets. And it's only when they would block, okay, you know, it says you need to wait or you need to try again or something, that I then register with a, you know, internal poller and say, okay, I'm gonna wait. And then the I/O poller thread will actually then notify back to the task to say, hey, your I/O is ready, go try again, and it, you know, the task wakes up and continues. There is a little bit of a difference here with how Go does it at the lowest level. They kind of have a direct integration with their scheduler of sorts. So they'll kind of just say, hey, I'm going along, you know, I'm scheduling tasks, and oh, this one is empty. I'm gonna go see if there's some I/O work that needs to be checked, okay? So their poller is really just another task that gets scheduled kind of optimistically whenever a thread is available. So directly integrated with the scheduler. I think we could probably do something similar in Julia. I didn't want to have to mess with a direct scheduler integration, and so the approach we take in this package is we're starting a foreign thread. So it's just an OS thread that we start ourselves in the package. Once you try to run Julia code on that thread, it adopts it and says, hey, thread, I don't know you. You weren't started by Julia. I'm going to put you in the foreign thread pool. So regular Julia tasks don't get scheduled there. It kind of, you know, keeps it isolated. And then we actually just run this very simple polling loop, okay, that says, hey, are there tasks that have parked themselves that are waiting for I/O notifications? Oh, I got the notification. Let me go reschedule this task to then continue doing its work. So that ends up being a lot simpler in terms of, you know, we're not passing a lot of data and callbacks and whatnot between this kind of polar thread and the actual Julia tasks. It makes it a lot simpler where this polling thread is very light. It's not doing a lot of work. It's essentially just looping around saying, oh, I got an I/O notification. Let me go schedule this thread or this task. So that's, I'm not, you know, doing the slides like what I'm talking about. That's what I just talked about. But essentially, so in Rezo itself, this is kind of an architecture of like what's all inside of it, except for the top layer. So we have native OS socket code, cross-platform, so Linux, Windows, Mac OS. We kind of manage creating those sockets and doing the network operation primitives ourselves. We have the KQ, ePOL, and IOCP, so that's kind of the I/O notification layer. We can register basically the file descriptor. We get notifications when the I/O readiness kind of flags. That's what the Polar foreign thread is kind of waiting on and triggering. The I/O poll layer is that Polar thread, so that's kind of managing all of the parked tasks and their registrations, and then doing the rescheduling. And then we build the TCP and TLS layers on top, okay? So this is where we actually take those underlying sockets, we're doing the TCP on top of them, where we're providing kind of a sockets-like interface. So we have very simple APIs around that. So the exposed kind of public surface of the package is just the TCP module and the TLS module. You get two different ways with the same, basically, API of how to work with sockets, either TCP-based or full TLS on top. So, for example, in the TCP, you can start a server. You can say TCP.listen. It's very simple. You can then say TCP accept on the listener to get an incoming socket. You can also do TCP connect on the address, and then you can write to that socket. You can do close write, read, that kind of stuff. So it looks similar in ways to the sockets library. There's a lot of similar concepts. It just tries to keep a very simple API there for the TCP layer. And then the TLS is almost exactly the same API-wise. There is a little bit of connection state here, so we can actually see like the ALPN protocol that got negotiated through the TLS handshake. There's some other configuration there when we can provide like the cert files, the keys, different parts of the protocol that we can configure, algorithms, cryptos that are allowed or not. We do have a native TLS implementation as well as part of this layer. So we use the OpenSSL JLL library at the lowest level for the crypto primitives. So that's the only piece left that's not pure Julia, where we're actually calling down to do the encrypt decrypt on the packets coming through. Everything else is native TLS, and it's kind of all threaded through in the same kind of API. So we can do a quick live demo, obviously. This is not like the most exciting demo, but essentially here we're loading Rezo. We're going to start a TCP server. We have a channel. We're going to pass some data, and we're going to accept a connection. We're going to echo back. We're going to connect to the server, and we're going to set a deadline. Okay, so a timeout. That's how we're kind of setting those. That's natively integrated down. And then we're actually going to trigger that deadline as well. So like I said, this is probably the most boring demo you're going to get today, but we're going to show it anyway because it's exciting. It's fun. So we had our TCP echo that we had come out, and then we actually triggered the deadline. It took too long in the second case, so we had a deadline error, a deadline exceeded arrow that got thrown. Essentially, that deadline is threaded all the way down through to the lowest level. So basically, it will fire and schedule that task with the error instead of the I/O notification, and that's what kind of gets bubbled up while the I/O gets canceled. This also works on the TLS side. So we're going to load some certs here. We're going to say the protocols that we support. So we say we support H2 and HTTP1, and then we're going to do essentially the same code here. And this also works just natively with TLS. So I can just start a TLS socket, read and write with it, and kind of negotiating protocols and kind of move on from there. So that's fun. That hasn't been easy to do for a long time in Julia. And the performance is great. So this is a benchmark. I reran everything last week just to make sure everything was up to speed and up to date. So the benchmark, I'm running on one of these beefy cloud machines. It has about 30 gigabits of network bandwidth. That's for the outbound, so that should be the put. So just so it's clear, that's why the download is higher. When they state the numbers, it's for the outbound bandwidth. So we're almost, pretty close on saturating the bandwidth outbound, and then on inbound, it's much, much faster. But the benchmark is essentially Rezo for the network layer. We have the new HTTP 2.x releases on top of that, and then we have the cloud-based and cloud store packages. So those are kind of built on top to do the, this is where we're basically starting with 64 threads, and then we're putting a lot of objects just straight into Azure Cloud Storage, getting them back out. So how fast can we do that, right? And the performance is great. Like I said, this is a bit of an extreme benchmark. I don't expect a lot of actual use cases need this kind of throughput, but it's kind of been a personal challenge for me for a long time that I would love that we can do this. And we actually beat a lot of kind of other tools out there. There's some Go, S3 copy, the Azure kind of CLI itself that does this Azure copy thing. We're like way faster than them. It's fun. It's fun that we can push the performance this well. And then kind of personally, I've obviously mentioned the HTTP case. So the new HTTP 2.0 and beyond releases are all based on Rezo underneath. There's also a number of other packages where I'm starting to use this. So I just released a native Julia Postgres package. So we will start a TCP or TLS Rezo socket and read and write the binary Postgres protocol directly. And that works really well, and we don't have to deal with any C libraries. I also have a Redis client, a NATS client, some of these other, services where we're interacting with a server and we need TCP or TLS sockets, just kind of natively with high performance, and it's working really well. So this is a little bit boring. Not a lot of people really care about this level of the stack. But it's been a lot of fun for me. It's been a personal goal of mine for a long time to have something that feels really nice and that I can rely on and use in a variety of ways. So that's Rezo.
I'm sure, well, now it's loud. I'm sure there are some questions. Maybe I just run up.
Yeah, it looks beautiful. Should we just replace libuv with this?
Possibly. It doesn't do any UDP yet. I don't think that'd be too hard to add. It doesn't handle some of the other libuv things that we're using, kind of the process and some of the file operations and all of that. But I think for the TCP socket side of things, I think it really works well. And I think it follows kind of Julia's model really closely. So like I said, doing that initial setup and the feel and the ease and the simplicity just felt really nice.
Next question.
So unintended follow-up question. Given the lack of UDP, I assume Quick would also rely on having UDP. Once we have UDP, which seems like it should be pretty easy because UDP doesn't have anything in it, how horrible would Quick be, do you think?
It's a good question. Part of what made, I think, my own confidence in the Rezo stack as it is was partly having the extensive Go test suites that we could also port over, and porting those first, then porting the code and saying, hey, these all run and these all work and these are all correct, right? That helps, right? Because we know that there's been thousands and thousands of hours poured into the Go architecture and their test coverage and the issues they've seen. That helps the confidence a lot, right? So I think it would be a matter of finding something where we could have a similar amount of confidence, right? I don't think it'd be too hard to layer it on top. We kind of have the general architecture there. But I think it's a matter of can we find a really solid fuzzing testing suite or some kind of reference implementation that we can check things against, right? That's always been part of the challenge on the HTTP side as well, and the WebSockets. And can we find these reference testers out there that really can help harden and make sure we're doing everything that we want it to do?
We have another question here.
Do you expect to keep this aligned with the Go implementation going forward? keeping that checked for bugs so that you can port them over, or do you think this is like now a fork in the road and Rizzo goes one way and they go another way, but you would do your own thing?
I think it's a mixture of both. I would say it's a standalone implementation at this point. We do have to kind of manage and change certain fundamentals based on how Julia works versus Go. I think if there happen to be, changes or bugs on the Go side, obviously we should, there will probably be cases where we'll want those fixes on the Julia side. But yeah, I think it's a mixture of both.
Okay, we have another question from here.
So, very nitty-gritty question. You mentioned that the Polar has to wake up specific tasks. So what happens is, like, when a task says, "Hey, I want to write some bytes to a socket," does it register itself? Like, how does the completion model know which task to wake up? And basically, what's the architecture? Are there some queues or a dictionary or something of that kind?
Yeah, it's a registration list, like a lookup based on the file descriptor, read or write. And we have, we ported the Go model there where it has like a certain locking system around the different sides of that file descriptor, read and write. But then essentially when the notification comes in, I have an easy lookup to know who to reschedule. Yeah.
Okay, another question here.
So I wonder, how nice does your own Polar play with the existing Julia scheduler? Because I'm under the impression that the more idiomatic thing is just to let Julia scheduler run the scheduling. So why didn't you do that? And do you think it's possible to do that?
Yeah, I kind of talked about that right at the beginning. I think it is possible because that's kind of the Go model is let's just optimistically try to check the Polar notification queue and reschedule stuff in the native scheduler. That felt messier to try to do when it's just trying to like prove this whole thing out. Whereas just starting a foreign thread that stays completely separate from the rest of the Julia scheduler is a lot easier, right? We just run our own thing, nothing ever touches it, nothing ever runs on it. The allocations are basically none. And so it's a very light, like you don't know it's there kind of thread that its only job is to like, oh, you need to reschedule, you need to reschedule, you need to reschedule, right? And rescheduling means hand it back to the Julia scheduler to then, figure out which thread it should run on and do its normal thing. So it's not really doing scheduling itself. It's, I need I/O, I'm gonna wait, and then I wake up magically and the Julia scheduler helps me know where to go.
Yeah, we have another question here.
So I may have missed this in the talk. Did you benchmark against the AWS libraries? How did it fare against that?
They were very similar. Yeah, I did a couple different benchmarks where it was like the native C libraries, Julia wrapping, and then like a native, like a pure Julia port of the AWS libraries. Performance was very similar. And so I think they also can reach this like very high level of saturation at the highest levels. And then on the Go side, it's up there as well. I think it's a matter of like, if you have a clean model, you can pretty much get that saturation as long as you don't have like weird bottlenecks, somewhere in the line.
Yeah, I've been really disappointed with the downloads performance. The idea there was always like, you hook up the two schedulers, like the libcurl one and the Julia one, the libuv one, and then the scheduler should, cooperate and get great throughput, and then that's not at all what we get. So I don't know. It might be a smaller order than replacing libuv to just like replace downloads with this at least.
Yeah.
So.
Yeah.
Okay, are there more questions? If not, let's thank the speaker again. And since we need to cancel the first talk, we now have a coffee break for 15 minutes and see you back like in 3:45 here in this room. Thank you very much. show you like a sign.
Danke vielmals.
Ja, gerne. Danke für den Talk. Okay, right on time. Our next speaker, let me introduce to you Nikolai Bielefeld. And he wants to talk about convolution interpolations .jl. Take it away, Nikolai, please.
Can you hear me? Yeah, good. Yeah, I want to talk about my package convolution interpolations.jl. It's a package for high-order interpolation and differentiation and integration, and it can also do some smoothing. My name is Nikolai. I'm an independent researcher. This is not part of what I do in my day job, so it's just for my spare time. So what does this package do? Everything it actually does is it takes one of these kernels that I show here, which is a new family of kernels which I developed. It's the blue one is kind of the original. It's a partition of unity. That means the integral sums to 1 from minus infinity to infinity. And that means when you use it for interpolation, you always get the correct value. But then you can also use it for differentiation. If you differentiate the blue curve, you get the yellow curve. And then you can, instead of convolving the blue kernel, you can just convolve the yellow kernel to get the differential, to get the derivative of the signal in question. And then I'm not sure if anyone else has done this, but if you take the integral of the blue curve, you get the green curve, and it's not really a kernel, but I still call it a kernel because it's actually unbounded in both directions. But if you convolve the green kernel with the signal, you get the integral, but you have to take a difference to get the definite integral. Then why does it work quite well? I think part of the reason is that the spectra of the kernels are very nice. You can see here that the black B13 curve, it falls off very, very steeply after the ideal sinc function. Then there's some convergence here. For the uniform kernels, they converge something like 7th order, and that means the B13 reaches machine precision around 1,000 samples on Runge's function. But then there's one surprising thing that I haven't described in the README yet, but actually the non-uniform kernels converge even faster. And that happens because when you have non-uniform samples, what I do is I enforce the order of the kernel through a van der Monde projection, and that means that the asymptotic order of convergence is the degree plus 1, and then when you have a B13 that's a 13th degree polynomial, it actually converges at the rate at 14. But B5, as you can see, it becomes a little bit slower than the 7th order of the uniform one. Yeah, and then I want to show some demonstrations. Is that large enough? Okay. Wait. Yes, I'm going to use plots to show this, and then I will have this function just to test, and we will sample it 25 places, and that's our y. Then we will construct the interpolant and plot. No, we will make the fine grid first. Then I will plot the samples. See, that's the samples. Then I will plot the interpolant on the fine mesh. See, that's it. And then I will plot the true function. That's basically on top of each other. Yeah. Then we can also do derivatives, and that's like I explained before. That happens by taking the derivative of the kernel and convolving it with the signal. So these are the analytical derivatives of the function I showed before. And then we only give the convolution interpolation access to the basic function, and then we just write derivative 1 or 2 to get the derivatives, and then we plot the first derivative according to the interpolation package. So we get a smooth derivative, and then we plot the analytical values, and they are right on top. And then we take the second derivative and plot the analytical values. So also right on top. And then we can also do integrals by convolving the unbounded kernel that I showed before. And actually, since it's unbounded, you have to convolve the entire domain. But then I pre-compute all of those sums. So in 1D, you have to pre-compute the sum for every point through. And in 2D, you have 4 corners, 4 strips, and the center region. So, and in 3D, it gets even worse. So I didn't go higher than 3D, but you can imagine in 3D, you have like a box where you do the convolution inside, and then you have to compress the domain onto those faces and onto those edges and onto those vertices of that box to get the actual integral. And the reason I did that was to get it fast. It takes a little more to set up, but when it's set up, it's fast to evaluate. So we set derivative equal to -1 for the antiderivative. and then take the integral as a difference to get the definite integral. And it should be 2. The integral should be 2 for that function. And that's quite close to 2, at least from 25 samples. And the integrals also converge like 7th order. So if I put more samples, it's faster. Then we can also do non-uniform, as I mentioned before, that actually converges more quickly. And we can do non-uniform derivatives. Here I'll do a non-uniform grid and a 4th derivative. So this grid is non-uniform, and we'll take this nice function that's easy to differentiate and take our samples. And then I'll just confirm that we can actually work with this non-uniform grid. And then also the fine grid. Then we have the 23 samples, non-uniform. Those are the samples, as you can see, non-uniform. And that's our interpolant, also hitting right on top. And then we have the true function, looks like that. And then the 4th, then we take the fourth derivative by setting derivative 4. You can read in the README how high they actually go, but the highest derivative they can do is 7th derivative. But of course it becomes more and more unstable because it kind of blows up for some functions. Then we take the complex exponential derivative here. That's the analytical value. And then I plot first the interpolant. That's the 4th derivative. And then the analytical values are right on top. Then actually the last thing I want to show is that it's actually, now I've been showing 1D, but it goes to very high dimensions, as high as your computer can handle, basically. You can choose for each dimension which kernel you use. For example, here I take this function sine times cosine, and then I say I want the 2nd derivative in the x direction and the integral in the y direction. And the way it works with the integral is it's always there's always a constant which can move the values around, so it's always like fixed to the left side with the integral. That's how I made it, just so it doesn't flow around. But then you can take the derivative and the integral and plot it here. That's from the samples and the analytical values. Yeah, that was maybe a bit fast, but yeah, that's all I had, actually. I hope there's some questions.
Okay, thank you very much. Are there some questions from the audience? Yes, wait.
Great talk. Did you find any edge cases for families of functions that didn't do particularly well in the interpolant when you compared it to the analytical?
Yeah, of course, if you have a discontinuous function, because the assumption with these kernels is that the underlying function is continuous. So, I also have there is one kernel which I developed, which is just it's called A0 in the package. It's basically made for discontinuous signals, so you can use that if you know beforehand. That's yeah.
Are there other questions? Yes. Second.
Thank you. Yeah, thank you for that. I think these kernels look amazing. I was wondering, could you explain the principle behind how you derive these new kernels?
Yeah, good idea. The basics. To be honest, it's been a long time since I did it. I've mostly just been building on it. But what I did was, I basically took. There was the basic paper from R.G. Keyes from something like the 80s, where he derived very what do you call it? Very strict. He showed how he derived the cubic kernel, and then I found another paper where they tried to expand it to higher orders. That's the kernels in my package. That's called that I call the A kernels, because they did expand it to 7th order, but seventh degree, but they were still like very low order in the convergence. So basically what I did was to take the principles of Keyes and use SymPy to build what you call Taylor series, term by term, symbolically, and then solve the system. And then I basically did like I did a search, manual search. I just sat there for weeks searching for kernels. So, and the way I selected them was to do, I solved the system to find the kernel, then I look at the spectrum, how it behaved around the top of that. If the further it went out before it fell down, I valued that higher, and also what was it? There was a way, I found a way to get the degree of the Taylor series from when it was automatically derived, based on when it vanished. That was how, yeah. So, but actually, I should explain more, because you have it's a piecewise polynomials. So this looks like a continuous function, but what you do is you say it should be flat at the origin, and that means the first derivative should be 0, the third derivative, I believe, also should be 0, and the fifth, and so on. That was what I learned from the second paper I mentioned. And all of the joints, it should hit 0 everywhere at the integers. And that's because if you slide it along a signal, consider that, then it should hit every point exactly. And that's what it does. And I should remember to also thank you, Mark, Because you told me to use the, I don't even remember the name, but the efficient way to evaluate a polynomial. What's it called? What?
Maybe a honor scheme?
Yeah, honors, yeah.
Okay, there are more questions? Just need to run through the lecture hall.
In your code example, could you show what it would look like for a discontinuous function?
Yeah.
So let's say it's 0 and jumps to 1 at like 0.5 or something.
X. X less than 0.5. Oh. Oh, shit. XE. That worked. Then I should do like, need to pay. I should be just plotted first. Actually, yeah, I haven't tried that one before. What I've tried before is a spike, and that integrates to a signal like that, but this one, it should grow like this, right? I'm not sure what it will. And then derivative. Plot. Is that right? I don't know. That doesn't look right, does it? No. I'm not sure if that's right.
Looks kind of right, isn't it?
Yeah.
Are there additional questions? So if not, maybe I can ask a question, because we have 2 minutes left, a couple of minutes left. You showed that you can do this in multiple dimensions, and you essentially showed that you define a grid where you evaluate a multivariate function and then doing the convolution interpolation on this multivariate function. Would it be possible doing this on not on a grid, but on kind of scattered data? So the data can be aligned, but the different dimension has different numbers of nodes with some holes in there. Would this be possible?
I have an example with that in my README, where I have a function that can take that kind of scattered data and put it just nearest neighbor, just using nearest neighbor, and then you get like a noisy signal, but then smooth it afterwards, and then you get something close to the real signal.
Okay, I'm asking because there is a theory called unisolvent nodes, where you do multivariate interpolation on high dimensions by like choosing a grid, which is not a grid, but choosing nodes in a multidimensional hyperspace, which are not on a grid. So they leave out some nodes in particular positions. And the question would be if, and it scales better than like the just or it lifts the curse of dimensionality in a way. And converges better. That's why I'm asking this question, because this would actually allow to scale these types of interpolations to higher dimensions quite good.
But they scale quite well, because I use, what do you call it? The fact that you can apply them one dimension at a time. So I have a function called convolution resample, which does the whole thing just by one pass through. It's what I showed here. It constructs the interpolant and then evaluate. But the other one, it just takes the array and outputs another array. But I don't know about what you're talking about.
Yeah, we can discuss this after the session if you like. Okay, if there are no other questions, let's thank the speaker again. Let's see.
There's a second speaker, so if he can use the microphone, that would be nice.
Oh, okay. Yes.
But the second speaker isn't here yet.
Oh, okay. So we try to adopt live. So we try to adopt live.
Yeah.
Just rotate to the thing. Okay. So does it work? Don't see the slide yet. This looks quite well. Yes, our next speaker is Arno Struven. I mean, we can wait for 3 minutes because it was told that the talk is actually given by 2 speakers and the second speaker not yet arrived. So I would like, okay, then it's fair to just wait for 2 another minutes. Yeah, sure. want to use the time to announce something till the talk starts. I get the information from the main organizers that we will have a photo in front of the Alta Mensa after this session, and I should encourage every one of you to more or less rush to the Alta Mensa because we want to take the photo before the keynote, and we want to start with the keynote on time. So please, after the session, you're allowed to actually run away directly to the Alta Mensa. Thank you very much. I think we should start with a talk. The second speaker will arrive in a couple of minutes, so it will be fine. Let me introduce the next speaker. It's Arno Struven, and he gives the talk together with Sebastian Miklucha Campeanu. Really sorry for mispronouncing that. And they will talk about deep adaptive design for experiments for dynamic systems. Please take it away, Arno.
Thank you for your introduction. So indeed, this talk is about experimental design, particular for dynamical systems. And we will be using some techniques from deep reinforcement learning to do this in an adaptive way. This is joint work between me, Arno Strauer, and Sebastian. Sebastian is still rushing over here from another session, so he should be here soon. Hopefully, I won't have to stretch my part too much. Yeah, so I did the design part of this project, and Sebastian helped me out with some of the trickier Julia programming aspects. I'm primarily working at Pumas AI, and Sebastian is at Julia Hub. But as you can see, neither of us can get it across our heart to completely ditch our academic affiliations. So I assume that most people here are not too familiar with experimental design. So I'm going to start with a very general overview. So in experimental design, we have some data, which are unknown parameters that we are trying to learn about. Then we have U, which is the design. So think of it as anything in the experiment which you can tweak to your desire. And then we have the Y, which is the measurements, the observations coming from the experiment. This whole talk follows the Bayesian paradigm, because as you will see, that will make it much easier to do adaptive experiments. So in Bayesian statistics, you always have a prior distribution which represents your state of belief of what the correct parameter values for the data might be. And then after the experiment, you use Bayes' rule to update that belief based on the information that is inside of your observations. And then in Bayesian experimental design, the entire goal is to pick the U in such a way that the Y, the observations, carry a lot of information about the data, such that the posterior shrinks as much as possible, becomes as sharp as possible. Okay, that probably sounded quite abstract. Can we make it a little bit more concrete by looking at an example of a dynamical system? We will be working here with a bioreactor like this. What do we have in this bioreactor? Well, the evolution in time of this bioreactor is governed by differential equations, as you see over here. In the bioreactor, you have biomass. You can think of that as little creatures that are inside of this reactor. Then there is also substrate in the reactor, which is the food that the biomass consumes. Okay, then the experimental conditions, the U here, that we can control ourselves, is how much food, how much substrate gets pumped into the reactor over time, and this will cause the volume of the reactor to increase. Exactly how the biomass consumes the substrate is governed here by this famous Monod equation, and this equation says that at first, if you give the biomass more food, they will grow more quickly. But as you keep giving it more and more food, the growth rate will not increase indefinitely. At a certain point, there is an abundance of food, and it is no longer the limiting factor for growing more biomass. But the exact mechanism of at what point inhibition starts occurring, of how fast they grow, that is not completely known. There are two unknown parameters here, the U max and the Ks. And then the goal of experimental design is to pump food into the reactor in a clever way, such that we can learn as much as possible about the U max and the Ks, which is the unknown parameters data here. Okay, I hope that makes it a little bit more concrete what the goal is for experimental design. Okay, so I said, goal is to make the posterior as sharp as possible. But what does that exactly, or what does that mean in mathematical terms? Or what do we use to quantify sharpness of a distribution? Well, what people in the literature have settled on is using entropy. So entropy is a measure of disorder. If you have a completely flat distribution, no data is preferred over any other data, then that is a distribution with maximal entropy. We don't want that at all. We instead want entropy to be very low, and this will mean a very sharp posterior distribution. However, there is one issue here with using entropy directly, and that is that you need to fill in the Y, the observations, to be able to evaluate this equation. And when you are at the stage of planning your experiment, you of course don't know yet what your observations will be. Okay, so how do we get around that? Well, what we do is we average over all possible observations that might occur from your experiment according to the prior distribution that you're using in Bayesian statistics. So this is why Bayesianism is so popular in experimental design. It is so that you can here provide a rigor or a principled way of evaluating or for providing these observations which you need to evaluate the entropy. Okay, there is a technical note here in that all the equations I've wrote down in the slide are about precisely learning the data, but it is often more realistic that you're only interested in learning a subset of the data. So for example, we were interested in these parameters from the Monod equation, but it might be that you have other nuisance parameters. You might, for example, have to estimate the variance of some noise. You might have to estimate some unknown initial conditions, and yeah, you have to estimate them, but you are not necessarily interested in estimating them precisely. And then if you do that, the math becomes a little bit more involved. I'm not going to go in detail about that. If you're interested, you can read this paper down here. Okay. But what is the issue with doing experimental design using this entropy criterion? It is that it is very expensive to evaluate. So we already saw here, or you can do some algebra on this entropy equation and rewrite it like this. This is already a little bit easier to evaluate because it no longer has the posterior distribution in there. It still has this observation, or still has this expectation over all of the observations outside. And even on the inside, there is still one tricky thing left over, and that is that you have to evaluate here this log P of y, which is the log evidence, basically. And to be able to evaluate this evidence, you need to calculate another integral. So we have an outer integral coming from this expectation, and an inner integral coming from evaluating this evidence. And if you do both of those things with Monte Carlo integration, you end up with a double for loop, a nested for loop. So to be able to evaluate this criterion for a differential equation model, you need to solve a lot of ordinary differential equations. Okay, so far I have been talking about what can be called static experiments. So, for example, here we have an input sequence U1 through K. What does that mean? Well, think of U1 as the amount of food you pump into the reactor in the first hour. U2 as the amount of food you pump into the reactor in the second hour. Okay, but then you can do something adaptive here, because the amount of food that you pump in the kth hour actually can condition on the history of everything that you have already observed so far, and of your previous experimental conditions that you have chosen. That's what adaptive experimental design is all about. You are adapting your experiment based on everything you have measured and inputted so far. And if you then write down the math of that again, you end up with this very complex dynamic optimization or dynamic programming problem. And what people have been doing historically as an approximation, as a workaround, is that they instead just myopically optimize one experiment ahead, and then recalculate the posterior, and then do that in a loop, update the posterior, calculate one experiment into the future, but not look very far into the future. But what we can instead do is to borrow some tools from deep reinforcement learning, where instead we can optimize over policies pi. And a policy pi is some function which maps the history to the next input, and then you can optimize in this policy space by minimizing over all of the pi to find the best policy. But of course, this is a minimization in a function space, so that's very tricky to do. But then this is where deep learning pops up, because you can just parameterize this policy with a neural network, and then it becomes gradient descent for the parameters of the neural network. And this has the great advantage that you don't need to recalculate the posterior as the data is rolling in. You can do all of the training offline in the lab, and then when you're actually in the lab, when you're actually performing the experiment, you just have to evaluate the neural network. So one heuristic way of thinking about that is that during training, you are simulating tons and tons of data according to your prior distribution, and your neural network kind of learns what good, or kind of memorizes what good experiments are for that data. And then when you are actually performing the experiment, you can just evaluate the neural network, and it will have memorized what a good policy is. Okay, so this is just to say, to be able to do this, you need to solve a ton of ordinary differential equations, preferably in parallel. And even if you do this on one of those expensive H100 GPUs from NVIDIA, it still takes about 15.4 seconds to do one step of gradient descent. And this is why it is probably a good idea to have an efficient implementation of this in Julia, which is what Sebastian will continue with.
Thank you. So, as Arno was saying, we need a very efficient implementation that is able to parallelize on the GPU as much as possible, so that we can so that we are able to actually do this optimization problem in a reasonable time. So, how did we implement this? We started with describing the policy in Lux using the layers provided there, and then we are using the reactant integration to be able to do not only the parallelization on the GPU, but also for the automatic differentiation via enzyme. For the differential equations, we have implemented a Runge-Kutta-4 method manually, but we also tested the simple DiffyQ with the low-level stepping interface, and that works essentially unchanged. And for the optimizers, we are using optimizers.jl for stochastic gradient descent. So, as we saw earlier, we have a lot of ODs to solve in parallel, and we also have to take gradients of that. And in order to do this efficiently, we need the reverse mode automatic differentiation. And this needs to run the program forward and then also backwards. And for the backward path, we need to remember what we did in the forward path. And essentially, because we discretize our dynamics using, for example, Runge-Kutta-4, essentially this unrolls the entire integration into essentially a giant piece of memory that we need to remember for the backwards path. And we can do an estimation of how much RAM would we need on the graphics card to be able to even store this, let alone being able to do anything compute-wise with this, but just storing this. And for a simple case of an ODE with 3 states and using float 32, naively, without doing any optimizations, we reach more memory than any available commercial card has currently. So this essentially needs optimizations for memory usage in order to be able to start solving the problem. The first observation that we have is that for training neural networks, we use stochastic gradient descent. And essentially, this needs the expectation value for the loss corresponding to the decomposed segments. And instead of doing one exact update at the same parameter and essentially the same weight for all the segments, we can do an approximation where we say that if there's a small difference between the weights, then we can do these steps in parallel at different ways. And this essentially almost half or even more than half the memory requirements. Depending on the batch size, we can even tune this to even be more optimal. As we can see here in the lower part of the screen, if we do this micro-batching optimization, we massively reduce the memory. But we can go even further than that. Reactant also has the ability to do checkpointing for us, which is essentially an optimization that trades memory for compute. Compute for memory. So we save a checkpoint at some point, and then we compute from that instead of storing the intermediary states. And this drives the memory requirements down to 7.5 gigabytes, which essentially makes it possible to even run on commercial cards or like laptop GPUs. And the nice thing about Reactant is that we can do this by just using a macro on a loop with a known size. Now, what are we optimizing the policy here? Essentially, we are describing the implementation of the policy, and the important takeaway here is that we have a positional encoding that essentially says that we cannot influence the future from the past. Essentially, the structure of the neural network is made in such a way that it encodes the temporal evolution of the ODEs. Because in a dynamical system, hour 3 and hour 11 are not directly interchangeable, and we need to encode this in the structure of the neural network. And as a comparison with other ways in which you can do this, usually people would use Python and JAX for this. And we also compared our implementation with Julia and Reactant against the solution with Python and JAX. And as I was saying, Reactant has some nice features around checkpointing, and we don't have to manually manage this as opposed to what we do in JAX. Now, on the benchmark results, we can see that Reactant can get us to almost 3 times faster, so 2.7 faster than the equivalent implementation in JAX. And a disadvantage here with Reactant is that the compile time is orders of magnitude more. Now I'm going to hand it back to Arno to continue with the results.
Okay, I will go quickly through the results because we are running low on time. So here we see for the reactor the adaptive policy in red versus 2 static baseline, one the entropy and another one using the Bayesian information matrix, which uses variance instead of entropy, long story short. So we see here the blue and the green, those are the static baselines, so they're always the same no matter how often you roll out the experiment. The red is the adaptive one, so that one is allowed to change based on the noise, on random initial conditions, so it is able to adapt. But we see in general the same trends are preferred, where in the beginning of the experiment you don't pump in too much, and then towards the end you start pumping in more food. We see here in the red indeed that the posterior is in general tighter than for the adaptive experiments compared to the static baselines. However, there are some experiments here where the mean of the posterior is estimated quite poorly in the adaptive experiment, and this is where your neural network basically outputs a very poor experiment because there was not enough training data available for that regime. Here is another example for a slightly different model where previously I said if there is too much food, the bacteria are not growing or the biomass is not growing faster anymore. But you can go to a different model where if you give it too much food, the food actually becomes toxic. And then here you have an experiment where either the food does not become toxic or it does become toxic, and then the experiment also adapts based on the true parameter values of your system. Then a final example here, we are moving away from the bioreactor and going for a DC motor. Here we see that using these policy methods, we are comfortably below the real-time threshold we need for providing the next experimental value, while the traditional method of re-optimizing the posterior and then myopically picking the next experimental condition, it becomes too slow to be able to perform in real time. Okay, then I'm giving it back to Sebastian to close it off.
So, as we mentioned, we have used simple DPQ and reactant with the low-level or stepping interface, but it would be nice to have a deeper integration with the SciML ecosystem and especially be able to use adaptive solvers and step solvers. And for this, I have been running some experiments to essentially create a reactant-specific formulation of some integrators, and currently I have an experimental version of SID5, an adaptive version of SID5 that can train a UDE. And if you want to learn more about this, there's a paper and the code available on GitHub. You can use the QR code to learn more about this. Thank you.
So let's thank the speakers. Are there any questions? Still some hands up. So I will take the opportunity to ask actually a question. The first question what I have is, can you comment on the scaling when you increase the numbers of unknown parameters? So when you increase them, what becomes the bottleneck first?
Yeah, so far we have only been able to stretch this to problems with, let's say, less than 10 parameters. There exist novel techniques that can stretch this to thousands of more parameters, but those are based on diffusion. So that's a novel technique in Bayesian inference based on diffusion, and you can also apply that to experimental design, but we have not yet incorporated that with all of the ODEs and so on.
If there's no other question, I would take the opportunity to ask another question. How does your system or your strategy works when you misspecify the model? So if there's some noise in there, for instance.
So, that is indeed another open problem in experimental design in general, that you always assume that your model structure is completely correct, and then that you are only doing inference for some unknown parameters. But often it is much more realistic that part of your model structure is also unknown or misspecified, as you say. And indeed, these techniques that we show you here are not directly robust to this. However, I have been doing some research about using Bayesian symbolic regression to be able to incorporate such a missing component to your system, and then you can also calculate some type of entropy of that symbolic regression, and then start applying these techniques on there. So it is possible to extend it in that direction, but people have not yet done that, and I think particularly for dynamic systems, that is the next thing forward that I'm working on.
Okay, thank you very much. If there's no other question, let's thank the speakers again. Pretty good. We are right on time. It's good. Also done? Yeah. I think we wait another minute just to give other people a chance to change rooms. Start for the next talk. Let me introduce the speaker. It's Abel Soares Siqueira. Hopefully it was pronounced right. And he wants to say something about what's new in BEST templates. So please take it away.
A lot. So olá a todos. Thanks for joining this talk. My name is Abel Soares Siqueira. I'll give an update on BEST template, which is a package we developed about 2 years ago. We presented in the Eindhoven JuliaCon. So I want to give a brief update and maybe just a little bit if you don't know about it. So the quick version, if you need to get out for the photo, for instance. So BESTI, the BEST template, BESTI is a quick way to adopt the best practices for package development. So, you know, generate a new package or get the testing, the documentation, all of that thing. There are new things now. A way to quickly create the package via known interactivity, a quick way to add new features, a specific single thing. We have many new features. We have a new CLI tool. And with that new CLI tool, we have a new agent skill that you can use to quickly adopt things. We have some new documentation for if you want to contribute to BESTI, either by yourself or using an LLM. Okay, so what is BESTI? In summary, it's an opinionated template. When we created a Tulip Energy model package, we got some of the things that we found interesting from Julia development, from package templates, for instance, and some of the other things that we develop in our company for research software. And we created this template, which is a bit easier to maintain than package templates, which was a main motivation to create it. One big difference is that it also applies to existing packages. So you don't need to create a new package and just copy everything. You can get your package as it is and run BESTI. And we are focused on these best practices as we consider them best practices. The opinionated part is essentially what we have recommendations per level. So this is like an adoption strategy, let's say. So we have 3 main strategies. The light one, if you're just creating a new package and you want to move. A moderate, which adds some friction, but not a lot, that will make you slow in development. And the robust, if your package has many, many users and many developers and you want to keep things in sync. We have also created, per demand, a tiny version, which is essentially no to every addition that we have for you. And we have things that are advanced, that are either experimental or too niche to be generally recommended. So in the back, BEST is supported by Copier, which is a Python package. And Copier is the engine behind the whole thing. So on our side, we have BEST, the template. We have you with the answers to what you actually want in your template. Those things together create the Julia package. And on top of that, Best is also a Julia package. So you can add a Julia Best template and say using Best template. And what you get in addition to using Copier is that because it's a Julia project, we can guess a few things and we can preview some of the things that are a bit annoying to fill by hand if you're using Copier directly. For instance, the UUID that you have to create for a new package. These are the three main ways to use Bestie. I'm gonna mention some of the new additions that we have. Most of these things are recent for the last 6 months. Probably relevant right now, add agents. So you can have a template for your agents, changelog based on the keep a changelog format. We have also the PandaBot. So if you haven't seen the PSA a few months ago, instead of using the compat helper, now you can use the PandaBot for your Julia compatibility, and that's much better. But also for the GitHub Workflows versions, if you want to update that with the PandaBot. We also have the check explicit import based on the explicit imports package. It's highly experimental, but it's there. We have some new testing strategies. So the normal way to use testing in Julia is already supported in Basti by default, but you can add some things on top. For instance, the test items package. I highly recommend the test items package. And one thing that we created, maybe not so useful anymore in the LLM context, but back then it was really important, is a command line a command line interface so that you can run the test item runner filters via the Julia -- project run. We also have added a file called cov for the coverage tests and various files that were restricted, that you did not have an option. Now they are behind some questions, so you can decide to add them or remove them per file. We have a few new interfaces. I separated them essentially in 4 kinds of way to interact with the package. The classic ways, so I already mentioned generate, apply, and update. And we also have copier copy, which is the Python way of using it. Non-interactive way, we have the new package quick and the add feature. The command line interface is best template on PyPy. It provides the same functionality as add feature. And the AI agent skills Bestie features. So a bit more details. If you want to use the full template right now, this was the same as it was 2 years ago, essentially. You can just use copier copy directly from Python, or you can use besttemplate.generate or .apply for your existing packages. You can update from previous versions. All of those things are supported by Copier. So essentially, there are a lot of people working out there in a larger audience developing these things. And then we have created this new non-interactive way called new package quick that just uses the recommended approach. So you just say, this is my package, this is my GitHub username, this is my full username, and then you can say which strategy you want to follow. The new thing that I recently added is this add a single feature. So what sometimes happens is maybe you are not ready to adopt the template yet, maybe you just want a single file, and you say, oh, I just want the PandaBot. How can I add only the PandaBot? So essentially we are hacking Copier by selecting one answer and ignoring all the rest of the files, and that allows us to say, these are the things that we want when you have this specific key. So it's a curated list of existing questions. We can add more if you have a specific need. Right now we have about 10 things in there. The Python CLI that I mentioned is essentially providing the same feature. It has a parity with the Julia version. So you can just say, using UVX, for instance, you can say Bestie list features to get everything, or Bestie add feature and the specific feature that you want. And as I mentioned, we have a skill for agents. maybe a few months ago, I was thinking about like, okay, I don't think BASTI is really necessary anymore because I can just say, please LLM, create me a dependabot file, and that kind of works. But then, do I trust that dependabot file? Who is using it? How do I copy it from an existing source? And then I essentially just created these skills that instead of just randomly asking the LLM for dependabot, you can say, well, add dependabot using the BASTI features, so then you know which file you're going to get. So some examples of things that you can do is please add dependabot to this repo, or check the available features that BASTI has, suggest something that would be good for me, or update my tests to use test item. You can just add the AI agent skill with npx skills add in this repo. And then finally, in an effort to try to get more people contributing, we have updated the documentation for adding new questions. So it's reasonably easy to create something new in the template. The template is essentially a folder in the BASTI template repo. And inside that folder, you're going to have a bunch of files with Jinja format. So you can add things conditionally based on the answers. And the questions are essentially a YAML block, 5 to 10 lines, specifying when that thing is added and what's the default, and some help and description for the user. The easy part is essentially that. You have a little bit more work by creating tests. So one thing that I like to have in BASTI is a kind of guarantee that when I'm using it, it continues to work and give some expected results. So there are a lot of tests for these features. It's not very hard to do that modification. You can copy from existing tests, like the test agent.jl. And optionally, if you want to create a feature, you can just update the features.toml file and some tests related to that part of the code. So thanks a lot for all the contributors for BASTI for all these years, and thanks a lot to the audience.
So let's thank the speaker. Are there any questions? Yes.
Hi, thanks for the talk and for the great package. I wanted to ask you, now that you can effectively have a main function in packages, have you thought of moving the Python CLI into the Julia package and just have one dependency that is Julia?
Yeah, I thought about that, but to be honest, I thought it would be harder. Because, not harder, but, well, maybe a little bit harder indeed, but it would be, essentially you have copier in Python, and then you have Julia for BASTI, and then you have the CLI, which would be using main. I think that's harder to maintain and slower than if I just have copier and then I have the CLI. And that's why I went in that direction.
Are there other questions? So I will take the opportunity to ask a question. As far as I remember, when I looked into BASTI templates the last time, the templates for CI/CD workflows are pretty much bound to GitHub Actions. Are there any plans to enable like other CI/CD tools like GitLab or CircuitCI, something like that?
Yeah, that's a good question. We do have an open issue about GitLab, essentially waiting for interested parties. So we did not use GitLab for the projects that we had, so because of that, essentially we did not implement it. So we are not opposed to having it, but there is no plans to actually implement it ourselves unless someone actually joins and supports that.
Okay. So, yeah, there's another question. Doing some sport today here.
Hello. How did you find contributors and how did the collaborations go?
How did I find, sorry?
Contributors, you have so many contributors.
Yeah, so that's the thing. With some poking, and a lot of the contributions are not in code. So one of the things that I like about this way of recognizing contributing is the allcontributors.org. So we recognize contributions that are creating issues or opening pull requests, but we also recognize just ideas and other kinds of contributions. We also had some funding. Again, I work at the Netherlands eScience Center. This project is more personal than work, but during some time, the eScience Center just did give me some budget to work on it. So a third of the people here are from the eScience Center.
Okay, if there's no other urgent question, we will thank the speaker again.
Thank you.
And I take the time again. Why is my microphone? You want to talk about leveraging Go in Julia, so please take it away, Martin.
Thank you. All right. Yeah, so this is JuliaCon, so let's talk about Go. Or rather, let's talk about how to interoperate a little bit with Go from Julia. I was sort of just, again, Googling around a little bit, and it doesn't, like, we do a lot of interoping in Julia, right? You can do C and PyCall and so on and so forth. I haven't found too much like prior art on Go, actually. But at Julia Hub, for a project, we sort of ended up doing a bunch of calling into Go from Julia. So I wanted to just share some of those lessons that we learned from there, in case it might be interesting for other people to do as well. Right. So first of all, in case you're not familiar with Go, then I mean, Go is this relatively simple, statically typed, compiled language. It's like heavily used, I would say, like in various developer tooling and a lot of like backends, and people have been writing microservices for websites and so on and so forth. It's really like the blurb there is from the Go website, and I pretty much agree with it, like having written a little bit of Go myself, in that it is very easy to read and write. It's quite simple. It's sort of like C, but like taking away all the annoying bits and like adding a garbage collector to make your life nice and that kind of stuff. Deployment with Go is like super nice because it just compiles everything into this one completely independent binary that you can just move between systems or put in a Docker image or something like that. It has good support for concurrency. You can do like asynchronous tasks very easily. And the last thing I want to like, and I'm going to come back to that, is, you know, especially when it comes to sort of networking and web stuff, various like protocols, networking protocols, that kind of stuff. You know, Go has, you know, a lot of big companies have invested a lot of money basically into this, and it's really robust, and they have really good support for like any kind of networking stuff that you may want to do. But so at Julia Hub, why did we actually need Go in this case? So in general, Julia Hub, we have like a backend, which is like the sort of standard microservices architecture. So we have basically a bunch of Docker containers that live somewhere and talk to each other. Some of those microservices are written in Julia. And the problem we had was we wanted to add in a new microservice, but we did not write that particular one. We wanted to like reuse an existing software component. The problem was, or the problem we ran into is, like normally your microservices probably are going to talk to each other using HTTP, and that's fine to do in Julia. This particular new microservice insisted that you have to talk to it over gRPC, which, if you're not familiar with it, is well, it's basically, let's say, like a different way of just having network connection and doing sort of these remote procedure calls to the service. It's based on protobuf, which is a way to basically describe your data structures, and then there's a bunch of code generation that happens for every target language where you want to actually start using those data structures and to actually serialize data over the wire, and then gRPC like builds on top of that and actually handles the sort of networking layer and the RPC layer. The point being is that gRPC support in Julia is unfortunately not great. At least wasn't like a year and a half ago when I started working on this project. And that is sort of one of the unfortunate takeaways still is like the Julia's web stack and all the networking stuff can still be a little bit immature in places. It is coming along, quite well in, Jacob's talk, for example, earlier and so on. But, there are still a lot of gaps, and gRPC was one of those. I do want to acknowledge, though, that there is a package that does gRPC in Julia, and over the past about year, there's been a lot of activity there, and it's gotten, as far as I can tell, much better. But it wasn't there a year ago when we started our project. So what was our solution? Well, gRPC in Julia, in Julia doesn't work, but in Go it works really well. So how about we make a shared library, write it in Go, which can do the gRPC communication super well, and then we just call into it to get like the data out and like send the commands over to that microservice that we want to control and query data from. And that's what we ended up doing. And what I want to talk about next is just like some of these patterns that we developed for that part where we actually interact Go with Julia. TLDR though, it actually ended up working pretty well. Right. So yeah, first question, does it actually work? Is this even a thing that you can do? And the answer is yes, absolutely. The way you do it, Go has this library called CGo, or like a mode of using it, or whatever you want to call it. Basically, it's a way to export. Use Go. It's Go's version of C-call. Basically, it's a way to have Go talk to C libraries, shared libraries, and also you can take some Go code, export functions, and compile it into a shared library, and then you can just C-call them, and you get the C ABI. Like normal Go functions, etc., it doesn't follow the C ABI, but you can enforce it. And then, in Julia, you just do a C-call, and it's pretty easy. Nothing too much to say there, to be honest. There is something to be aware of, though. Go is a garbage collected language. It has its own runtime, just like Julia, which means if you link this shared library to Julia, now you have basically two runtimes existing in the same process. That part is fine. The problem is if you would link another Go shared library to the same process, so you may want to wrap, for example, two different Go libraries or something like that. Having two Go runtimes in one process is not supported and can crash. So this is not something that Go supports, as far as I can tell from issues. So that's something to be aware of. In my opinion, the downside here is it kind of rules out this idea that you can make like an Yggdrasil wrapper for a Go library, and somebody else makes their Yggdrasil wrapper for a Go library. It just puts up the SO, and yet people just pull it in and use it, because you can end up with multiple SOs being linked against the Julia process, and that probably will explode, at least on some platforms. So that's unfortunate. But as long as you are the highest level consumer and you control the build of the SOs, like we are, then it works. What's next? So yeah, in general, Go has its own types. Julia has its own types, and then we have the C types in the middle, so you're going to have to map them up, but it's relatively straightforward to do that. This is not the full list, but that's one thing to be aware of. Another thing that we had to, those type mappings were for the very basic types. What we wanted to do was to be able to take more complex Go objects, like for example some structs with maybe arrays in them, et cetera, and pass them to Julia so that Julia could kind of take ownership of them. The problem, of course, is, again, you have these two runtimes. Go manages its own memory. Julia manages its own memory. So once the C call comes back, Go might just go and delete your object or something like that. So you have to somehow work around that. But C-Go actually has an answer to that. You can create these sort of handles, which Go implements as, it's actually kind of clever in the sense like in Go, there is just a global map, which is an integer to a Go object mapping. And you can just go and be like, Go, give me like a number for this sort of, it's not a memory address. You shouldn't be passing the memory addresses themselves back to Julia, but you can pass these handles, which are just these integers. The only thing is that now you're also responsible for the memory management here, as in like you have to later on come back and like free the Go object, otherwise it will stick around forever. So there is potential here for memory leaks and so on. So you do have to do this sort of C-level memory management by hand. Another neat thing in Go, you can do, it's usually, this is because Go is like statically typed, you don't usually care about this, but Go does support runtime reflection of its types as well. You can have like this sort of opaque Go object in your Go code, and you can then, there's this whole reflection library which allows you to be like, oh, is this a struct? Well, if it's a struct, does it have a field name, foo, that kind of stuff. So this is the actual function we were using to like, sort of a simplified version of the function to get the unpack fields in a struct, for example. So there is reflection, it works. Something else to know, don't panic when you're using it like this. So Go doesn't have exception handlings, but it does have panics. But if you panic within a C call that goes to a Go function, that's gonna just segfault everything. What you can do though is the Go does support kind of catching these panics a little bit. So a pattern that we ended up adopting was putting these defers and recovers on top of every C call that we do, so that even though normally Go code shouldn't panic, it's considered to be bad practice to have your code panic. Reflection, for example, does panic if you do something wrong. So just to protect yourself, we like consistently applied this pattern to every function. And then we were like sort of, you can pass back this sort of error object back to Julia. And as the very last bit, maybe, just to something to be aware of in Julia is, I'm just gonna hop over this one. So when you do C calls in Julia, it can basically lock up your thread, which can be a problem if the Go code that you're calling now is doing something long running. For example, it itself goes and does network operations or some disk operations. And so the pattern that we ended up adopting was, again, every like this sort of non-trivial Go function call that we wanted to implement, the ones that were actually doing these gRPC calls against that microservice, we wrapped those in, we did this sort of polling approach. So instead of like having the C call wait, the C call actually just kicks off a Go routine, which runs now like independently in that Go runtime part on its own thread, and we just go back and like poll until it has returned the value into a channel. So that means that the C calls are always like very, very short, and so never block. We actually ended up sort of, because we had kind of a callback from the microservice back into our own service, it started locking up the HTTP server because the threads got locked up, and so the HTTP server didn't accept any calls, but like obviously it never got the answer back, so everything kind of got locked up. So that was a fun bug to debug. Yeah. All right, so all in all, takeaways. Can you do this? Yes, be aware of the second runtime problem. I feel like there's probably a package in here to have these sort of patterns documented and hopefully reused, but something to keep in mind is because of the runtime issue, probably this can't be sort of CXX wrap style thing where like people would just like put Go libraries into Yggdrasil, unfortunately. So those would be my takeaways. With that, happy to take some questions if we have time before the photo.
Yeah, thanks to speaker. Are there some questions left over? Yeah.
Thank you very much. What would you recommend to someone developing a complex system with a bunch of intelligent agents, some of them being implemented in Julia? So not all the agents or services are in Julia, but you have a bunch of independent models, so they're not just one Julia code with a bunch of functions, they're all independent. what would you recommend to someone who probably might want to adopt your approach?
Would you also have like parts of it implemented in Go as well, or?
Not really. I mean, if I would think of Go as the actual middleware that handles the communication between the entities. Because imagine, for example, I have some agent in Rust, some other agent in Zig or whatever, and then a bunch of models and search algorithms in Julia. And I want to now wire all of them as a complex agent systems.
So what I would just say here is, like, if you have some sort of a controlling process, which would be in Julia, and you want to call out to Go for any kind of communication or orchestration or whatever you may want to do, then yeah, I would say you can adopt this for sure, yeah.
Are there other questions? Yes, please.
I don't really know Go, but did you see anything in Go you wish you had in Julia?
I would say the sort of static type checking is like a big thing, which will sort of save you a lot. And one thing I kind of really like in Go is there are now exceptions. So in Julia, you get these sort of random exceptions popping up, and you have like no idea where it's coming from. In Go, errors are generally, or like always, sort of explicitly handled with this kind of pattern that it, like, if it fails, it basically gives you a nothing, and you have to check an error object, and that's really good because like it forces you to always handle every error, and you do it throughout your code, and basically it's very hard to write this sort of code where you suddenly get some sort of an exception thrown and like breaking everything. So that's something I really love.
Okay, since we need to rush to the photo, I want to close the session. Let's thank the speaker again. Yes, and this was it for this session in the afternoon. Thank you very much.